Subscribe to the channel so you don't miss out on any of these videos. What happens when a star, much larger than our Sun, runs out of fuel? Well, sometimes it explodes in a violent event known as a supernova, releasing an incredible amount of energy into the cosmos. Now, imagine if that explosion left behind not only a remnant of the star but also something far more mysterious: a pulsar. This isn't science fiction, it's the story of the Crab Nebula, one of the most intriguing and enigmatic objects in our universe. The Crab Nebula, located about 6,500 light-years away in the constellation Taurus, is one of the most studied and observed remnants of a supernova explosion. But what makes it so special? What secrets are hidden within its swirling clouds of gas and dust? How does the pulsar at its core provide clues about the fundamental laws of physics? Let's take a deep dive into the Crab Nebula, uncovering its cosmic legacy and the secrets of the pulsar that continues to fascinate astronomers and physicists alike. Let's begin by going back to the year 1054. In that year, observers from Earth saw a bright light in the sky, so intense that it was visible even in broad daylight for weeks. This was the explosion of a massive star, which became known as a supernova. The supernova eventually faded, but what remained behind was something extraordinary: the Crab Nebula. Over time, astronomers learned that this was the result of a star exploding in a cataclysmic event, releasing all its energy and matter into space. But what happened to the star itself? The remnant of the star's core, known as a neutron star, was left behind at the center of the nebula. A neutron star is the incredibly dense, compact core of a dead star that has undergone a supernova explosion. In the case of the Crab Nebula, the neutron star at its center is a pulsar, a rotating neutron star that emits beams of radiation from its magnetic poles. This pulsar is the heart of the Crab Nebula, and its properties are both fascinating and mysterious. To understand the pulsar's properties, we first need to understand what a neutron star is. When a massive star runs out of fuel, it can no longer sustain the pressure that keeps it from collapsing under its own gravity. As the star's core collapses, it becomes incredibly dense. In fact, a neutron star is so dense that a single cubic centimeter of it could weigh as much as the entire human population combined. The core is so tightly packed that protons and electrons combine to form neutrons, which is why it's called a neutron star. But how does this relate to the Crab Nebula? The pulsar in the Crab Nebula is one of the most powerful and well-studied neutron stars in the universe. It spins rapidly, completing a rotation approximately 30 times per second. This rapid rotation generates a magnetic field that accelerates charged particles, causing them to emit beams of radiation. These beams are what we observe as pulses of light, and the pulsar's intense radiation gives the Crab Nebula its name. It's like a cosmic lighthouse, its beams sweeping across space, giving us a glimpse into the extreme conditions at the heart of a neutron star. But the pulsar's fascinating properties don't end there. One of the most intriguing aspects of the Crab Nebula pulsar is its age. The supernova explosion that created the nebula occurred over 1,000 years ago, but the pulsar at its center is still active, continuing to emit powerful beams of radiation. It's a living fossil, a remnant of a star that exploded long ago, yet still providing us with valuable insights into the nature of the universe. How does it continue to shine so brightly after all these years? And what is driving its immense energy output? One possible explanation lies in the pulsar's magnetic field. The magnetic field of a neutron star is incredibly strong, millions of times stronger than Earth's magnetic field. This magnetic field is thought to be responsible for the pulsar's continued emission of radiation. As the pulsar spins, it generates a powerful electrical field that accelerates charged particles to near the speed of light. These high-energy particles then interact with the pulsar's magnetic field, producing the radiation we observe as pulses of light. But there's still much we don't understand about the Crab Nebula and its pulsar. For example, why does the pulsar spin so rapidly? And why is it able to maintain such high levels of energy for over 1,000 years? Some scientists believe that the pulsar's core may contain exotic matter, such as quarks or other subatomic particles, that are responsible for its incredible energy output. Others think that the pulsar's continued rotation and radiation may be the result of complex interactions between the pulsar and the surrounding nebula. As we study the Crab Nebula, we're also gaining insights into the processes that govern the formation and evolution of neutron stars. The Crab Nebula provides a unique laboratory for astronomers to study these extreme environments, where gravity, magnetism, and radiation interact in ways that are impossible to replicate here on Earth. By studying the pulsar at the heart of the nebula, we can learn more about the fundamental forces that shape the universe and the strange, exotic matter that exists in these extreme environments. But the Crab Nebula isn't just a laboratory for scientists. It's also a symbol of the incredible beauty and mystery of the universe. Through telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory, we can observe the nebula's intricate structure, with its swirling clouds of gas and dust. These clouds are remnants of the supernova explosion, and they continue to expand outward into space, creating a stunning cosmic landscape. The Crab Nebula is a visual testament to the power of stellar explosions and the incredible forces at work in the universe. The Crab Nebula also serves as a reminder of how much we still have to learn about the cosmos. Despite being one of the most studied objects in space, there are still many unanswered questions about the nebula and its pulsar. What drives the pulsar's rapid rotation? How does the nebula continue to expand so rapidly? What can we learn from the pulsar's unusual properties that can help us understand other pulsars and neutron stars throughout the universe? These are just a few of the questions that scientists are still working to answer, and each discovery brings us closer to understanding the fundamental workings of the universe. Perhaps one of the most exciting aspects of studying the Crab Nebula is the potential for future discoveries. As new technologies are developed, we may be able to observe the nebula and its pulsar in even greater detail. New space telescopes and observatories, like the James Webb Space Telescope, promise to provide us with even more information about the Crab Nebula and its surrounding environment. As we push the boundaries of our knowledge, the Crab Nebula will continue to be a key object of study, offering new insights into the nature of stars, supernovae, and the extreme conditions that exist in the farthest reaches of space. The Crab Nebula is more than just a remnant of a long-dead star. It is a cosmic puzzle, a source of mystery and wonder that continues to captivate astronomers and space enthusiasts alike. Its pulsar, with its rapid rotation and powerful magnetic field, is a living relic of a stellar explosion that occurred over 1,000 years ago, yet its light still reaches us today. Through the study of the Crab Nebula, we're not only learning about the death of stars, but also about the fundamental forces that shape the universe. And as we continue to study this remarkable object, we can only wonder what new secrets the Crab Nebula will reveal in the years to come. The Crab Nebula's place in scientific exploration cannot be overstated. Over the years, researchers have leveraged this supernova remnant to investigate numerous astrophysical concepts, from the behavior of matter under extreme conditions to the dynamics of pulsars and neutron stars. The pulsar at the core of the Crab Nebula is a real-world laboratory for physicists seeking to understand some of the most fundamental forces of nature. One of the key areas where the Crab Nebula has provided valuable insights is in the study of neutron stars. These objects, formed from the collapse of massive stars, represent one of the densest forms of matter known to humanity. The Crab Nebula's pulsar is a perfect example of a rapidly rotating neutron star, and its study has helped scientists gain a deeper understanding of how these stellar remnants function. As we study the pulsar's behavior, we observe extreme conditions that simply cannot be replicated on Earth. The magnetic field, the rotation speed, and the energetic emissions all provide a glimpse into a realm where the laws of physics operate differently from what we experience in our everyday lives. One of the most perplexing features of the Crab pulsar is its energy output. Unlike other celestial objects, where energy is gradually depleted over time, the Crab pulsar continues to emit vast amounts of energy, a process that has been going on for over 1,000 years. This sustained emission is a mystery that challenges our understanding of energy conservation in the universe. To comprehend the pulsar's long-lasting energy production, scientists must delve into the complex mechanics of how energy is stored and released within the neutron star. Unlike a regular star, which generates energy through nuclear fusion, the pulsar's energy comes from a combination of rapid rotation and its intense magnetic field. These phenomena create a system where energy is not only conserved but amplified, producing the immense radiation we observe from Earth. Researchers have proposed several theories to explain how the Crab pulsar manages to keep its energy output so high for such a prolonged period. One theory revolves around the idea of magnetic braking. As the pulsar spins, it emits electromagnetic radiation, which causes it to lose rotational energy over time. However, the rate of this loss is incredibly slow, allowing the pulsar to maintain its rapid rotation for centuries. This means that while the pulsar is gradually slowing down, its energy generation remains high enough to produce the intense beams of radiation that we see today. Another interesting aspect of the Crab Nebula and its pulsar is its connection to the concept of pulsar wind nebulae. These structures are formed when the high-energy particles emitted by the pulsar interact with the surrounding material in the nebula. The Crab Nebula is an excellent example of this phenomenon. As the pulsar's radiation interacts with the surrounding gas and dust, it accelerates particles to near the speed of light, creating a web of energetic particles that extends outward from the pulsar. This creates the signature shape of the Crab Nebula, a vast and expanding bubble of high-energy particles that is continually fed by the pulsar's output. These pulsar wind nebulae are not only visually stunning but also crucial for understanding how energy is transferred from a pulsar to its surrounding environment. The study of pulsar wind nebulae like the Crab Nebula offers more than just a glimpse into the behavior of individual neutron stars. It also provides important clues about the broader processes at play in the universe. For example, the interactions between the pulsar and its environment can shed light on the mechanisms that drive cosmic particle acceleration. These insights are critical for understanding phenomena such as cosmic rays, high-energy particles that travel through space at nearly the speed of light. By studying how the Crab Nebula accelerates particles, scientists hope to uncover the secrets of these ultra-high-energy particles and learn more about their origins and behavior. As researchers continue to study the Crab Nebula, they are constantly refining their models of how the pulsar and the surrounding nebula work. Through the use of advanced telescopes and observatories, such as the Hubble Space Telescope and the Chandra X-ray Observatory, astronomers have been able to observe the nebula in greater detail than ever before. These observations have provided new insights into the structure of the nebula, the behavior of the pulsar, and the interactions between the two. For example, X-ray observations have revealed details about the distribution of high-energy particles in the nebula, while radio telescopes have allowed scientists to map the pulsar's magnetic field in unprecedented detail. Together, these observations are helping to piece together the puzzle of the Crab Nebula, revealing new layers of complexity and mystery with each passing year. Moreover, the Crab Nebula offers a unique opportunity to study the evolution of a supernova remnant over time. While the supernova itself occurred over 1,000 years ago, the nebula is still expanding, and its interactions with the surrounding space continue to shape its structure. By studying how the nebula has changed over time, scientists can learn more about the life cycle of supernova remnants, and how they evolve after the initial explosion. This information is crucial for understanding the broader life cycle of stars, from their birth to their death and the remnants they leave behind. Another important area of research related to the Crab Nebula involves the study of the neutron star's interior. Neutron stars are some of the most mysterious objects in the universe, and much of their interior structure remains unknown. The intense magnetic fields and rapid rotation of the Crab pulsar offer a glimpse into the extreme conditions that exist inside a neutron star. One of the major questions that researchers are trying to answer is what happens to matter under such extreme pressure and density. Does the neutron star contain exotic forms of matter, such as quark-gluon plasma, a state of matter that exists at incredibly high temperatures and pressures? Or does the interior consist of more familiar forms of matter, albeit compressed to unimaginable densities? These questions continue to drive research into the fundamental properties of neutron stars, and the Crab pulsar is one of the best objects to study in this quest for answers. The Crab Nebula also has important implications for the field of cosmology. As one of the closest and most well-studied supernova remnants, it provides a valuable point of reference for astronomers who are trying to understand the larger processes that govern the universe. For example, The study of the Crab Nebula has helped scientists refine their models of stellar evolution and the role that supernovae play in the creation of elements. The heavy elements that we are made of, such as iron and calcium, were forged in the cores of stars, and supernovae are responsible for dispersing these elements into space. By studying the Crab Nebula, scientists can gain insights into the production and distribution of these elements, and learn more about the processes that shape the chemical composition of the universe. Additionally, the Crab Nebula's role as a cosmic time capsule cannot be overstated. While the supernova explosion itself happened more than 1,000 years ago, the pulsar's behavior is still ongoing, offering a living record of the events that transpired in the distant past. By studying the pulsar's radiation and magnetic field, scientists can learn more about the properties of the material that made up the original star and gain insight into the conditions that led to the supernova explosion. The Crab Nebula is essentially a cosmic fingerprint, a snapshot of a moment in time that allows us to peer back into the history of the universe. As we look to the future, the Crab Nebula will continue to be a source of fascination and discovery. With new technologies on the horizon, such as the James Webb Space Telescope and the next generation of radio telescopes, we are poised to uncover even more details about this remarkable object. Whether it's exploring the pulsar's energy output, studying the nebula's expansion, or investigating the interior of the neutron star, the Crab Nebula promises to reveal new secrets about the universe and the forces that shape it. Each new discovery brings us closer to unraveling the mysteries of the cosmos and understanding the complex and dynamic nature of the universe we live in. The Crab Nebula isn't just a celestial object, it's a testament to the immense power and mystery of the universe. Its pulsar continues to shine brightly, a beacon of knowledge that will guide scientists and astronomers for generations to come. By continuing to study this extraordinary supernova remnant, we gain not only a deeper understanding of the forces that govern the cosmos but also a greater appreciation for the intricate and awe-inspiring beauty of the universe itself. As we continue to examine the Crab Nebula, it becomes clear that its significance extends far beyond its immediate scientific contributions. It serves as a reminder of the violent and often unpredictable processes that govern the life cycles of stars. The nebula's formation, following the cataclysmic event of a supernova explosion, highlights the incredible power of such cosmic phenomena, while its pulsar at the center represents one of the most extreme environments found in the universe. One aspect of the Crab Nebula's continued allure is the way it challenges our understanding of how the universe works on both macroscopic and microscopic scales. For example, the supernova that led to the formation of the Crab Nebula was the result of a massive star running out of fuel. Once the core of this star could no longer sustain nuclear fusion, it collapsed in on itself, causing an explosion that expelled the outer layers into space. This explosion, known as a Type II supernova, was not only incredibly powerful but also released a tremendous amount of energy and matter into the surrounding interstellar medium. This is where the Crab Nebula becomes especially intriguing. It's a dynamic environment filled with high-energy particles and radiation, all shaped by the aftermath of this explosive event. The remaining core, which became the pulsar, is an extraordinary object. The pulsar's rapid rotation and intense magnetic field are not just fascinating in their own right. They provide us with a glimpse into the end stages of stellar evolution, helping us better understand the fate of massive stars and the nature of the remnants they leave behind. When we think about the Crab Nebula, we're not just looking at a supernova remnant, we're looking at an ongoing process of cosmic recycling. The remnants of this explosion continue to interact with the surrounding material, creating a complex and ever-changing environment. The energy emitted by the pulsar, for example, accelerates particles to speeds approaching that of light, creating a cascade of high-energy cosmic rays that radiate out from the nebula. These particles carry with them valuable information about the conditions inside the nebula and about the processes that continue to shape the space around it. The Crab Nebula also raises profound questions about the nature of energy itself. How does the pulsar continue to emit such vast amounts of energy for so long? What mechanisms are at work within the neutron star's interior that allow it to persist in this state? Theories have suggested that the energy generation within the pulsar is closely tied to its magnetic field and rotational motion. But we're still piecing together the exact processes that govern its behavior. The study of pulsars like the one in the Crab Nebula pushes the boundaries of our knowledge about energy production and the fundamental laws of physics, particularly in extreme environments. Additionally, the Crab Nebula presents a unique opportunity for understanding the relationship between matter and radiation. The supernova explosion that created the nebula dispersed heavy elements into space, enriching the interstellar medium and contributing to the formation of future stars and planets. In a sense, the Crab Nebula is part of a larger cycle of cosmic rebirth. The elements released in the explosion will eventually be incorporated into new stellar systems, continuing the cycle of matter and energy throughout the cosmos. This connection between the death of a star and the creation of new matter is a crucial aspect of the Crab Nebula's legacy. The nebula also offers critical insight into the concept of cosmic time. As one of the most well-studied remnants of a supernova explosion, the Crab Nebula allows scientists to examine the long-term evolution of a supernova remnant. The nebula is still expanding, albeit at a slower rate than it did in the immediate aftermath of the explosion. By studying its ongoing expansion, we can better understand the processes that govern the interaction between a supernova remnant and the surrounding space. This understanding can provide valuable insights into the dynamics of other cosmic structures and phenomena, from the birth of new stars to the formation of galactic clusters. The Crab Nebula's ability to help us study such complex, large-scale processes makes it an invaluable object in the field of astrophysics. Every observation we make adds another layer to our understanding of the universe. For example, by analyzing the Crab Nebula's electromagnetic radiation across various wavelengths, from X-rays to radio waves, we can gain a more complete picture of the energetic processes occurring within the nebula. Each wavelength reveals different details about the nebula's structure and behavior, from the high-energy emissions near the pulsar to the slower-moving particles in the outer reaches of the nebula. This multi-wavelength approach is crucial for painting a full picture of the Crab Nebula and its inner workings. Moreover, the study of the Crab Nebula is not just a theoretical endeavor. The practical applications of this research can have far-reaching implications. For instance, the understanding we gain from pulsar behavior could lead to advancements in areas like technology and energy production. While we're a long way from harnessing the energy of a pulsar, the insights we gain into extreme magnetic fields and rapid rotational motion can have applications in fields like materials science, magnetic storage, and energy systems. In fact, the study of neutron stars and pulsars could one day lead to breakthroughs that we can't even foresee at this point in time. Another fascinating aspect of the Crab Nebula is its connection to the study of high-energy astrophysical processes. The high-energy particles generated by the pulsar and the nebula are a direct source of cosmic rays. These ultra-high-energy particles are a subject of great interest in the field of astroparticle physics. Understanding how cosmic rays are accelerated and transported through space can provide valuable insights into the fundamental nature of matter and energy in the universe. The Crab Nebula, with its pulsar-driven particle acceleration, is an excellent natural laboratory for studying these processes. Additionally, the Crab Nebula's pulsar serves as a unique tool for studying the behavior of extreme matter in a way that we cannot replicate on Earth. The intense magnetic field of the pulsar, for instance, is one of the strongest in the universe. This magnetic field is responsible for shaping the emissions that we detect from the nebula, and it plays a key role in the behavior of the particles within the nebula. By studying the pulsar's magnetic field, scientists hope to learn more about the nature of magnetic fields in general, and how they affect the behavior of matter in other astrophysical environments, such as the cores of black holes or the atmospheres of other neutron stars. Furthermore, the Crab Nebula's status as a relatively nearby supernova remnant allows scientists to conduct detailed studies over extended periods. This long-term observation provides unique opportunities for tracking changes in the nebula's structure, emission patterns, and particle dynamics. Over time, we've seen how the nebula has evolved and expanded, and these changes offer valuable data for understanding the processes that drive the expansion of supernova remnants, and the role they play in the cosmic landscape. As our understanding of the Crab Nebula continues to evolve, so too does our appreciation of the complex interplay between stars, energy, and matter. Each discovery we make adds to our understanding of the universe and our place within it. The Crab Nebula, with its pulsar and expansive remnant, is a testament to the dynamic, ever-changing nature of the cosmos. It serves as a reminder that even in the aftermath of death, whether it be the death of a star or the collapse of a neutron star, new life is always waiting to emerge. The energy released in these cosmic events continues to shape the universe, influencing the formation of new stars, planets, and even life itself. The Crab Nebula stands as one of the most compelling and awe-inspiring objects in the universe. Its pulsar continues to shine brightly, a beacon of knowledge that provides insights into the extreme physics of neutron stars, the acceleration of particles, and the behavior of matter in the most extreme environments imaginable. Through the ongoing study of this fascinating supernova remnant, we are not only uncovering the mysteries of the universe but also learning about the fundamental processes that govern all of existence. The legacy of the Crab Nebula, with its powerful pulsar and expanding nebula, will continue to resonate through the field of astrophysics for generations to come. With each new observation, we take another step toward unraveling the mysteries of the cosmos, one of the most exciting frontiers of scientific exploration. The Crab Nebula will always be a reminder of the incredible forces at work in the universe, and the never-ending pursuit of knowledge that drives us to explore the farthest reaches of space. As we continue to dive deeper into the significance of the Crab Nebula, we begin to realize just how pivotal this celestial object is in shaping our understanding of the universe. The Crab Nebula's central pulsar, with its rapidly rotating core, continues to challenge our theories about gravity, electromagnetic fields, and the fundamental forces that govern the cosmos. But it's not just the pulsar that holds our attention, it's the entire nebula, with its intricate structures and the way it interacts with the surrounding environment, that offers so much to learn. One of the most captivating aspects of the Crab Nebula is how it serves as a natural laboratory for high-energy astrophysics. The energy and particles emitted by the pulsar create an environment that is unique in the universe. As the pulsar spins at an astonishing rate, about 30 times per second, it generates beams of radiation that sweep through space like cosmic lighthouses. These beams, which we detect as pulses of radiation, are created by the interaction of the pulsar's magnetic field with the charged particles surrounding it. This phenomenon is called synchrotron radiation, and it's responsible for producing some of the most powerful X-rays and gamma rays observed in the universe. The pulsar's magnetic field plays an essential role in these processes. It not only accelerates particles to nearly the speed of light but also confines them within the magnetic field lines, creating a complex dance of energy and matter. Understanding how this magnetic field works, and why it is so strong, could provide us with valuable insights into the behavior of magnetic fields in other astrophysical environments, such as the regions surrounding black holes or the accretion disks of neutron stars. There's still much to learn about the mechanics of these extreme fields, and the Crab Nebula offers us an unprecedented opportunity to explore them up close. Furthermore, the Crab Nebula's pulsar continues to surprise astronomers with its unusual and fascinating behavior. Its rapid rotation, combined with its enormous mass and density, gives rise to a host of exotic phenomena. The pulsar's emission is not constant but fluctuates, which has led scientists to speculate that there may be a deeper, more complex mechanism at work within the star's interior. Some theories suggest that the pulsar's core might be undergoing some kind of internal instability, which could lead to even more surprising bursts of energy or changes in its radiation patterns. These fluctuations have yet to be fully understood, and their study is a priority for astronomers who hope to uncover the mysteries of the pulsar's internal workings. As we study the Crab Nebula's pulsar and its behavior, we begin to ask larger questions about the very nature of space and time. The pulsar, with its immense gravity and powerful magnetic field, distorts the fabric of spacetime in ways that we are only beginning to comprehend. How does the intense gravitational pull of the pulsar affect the surrounding space? Could its rapid rotation influence the curvature of spacetime in the vicinity, creating ripples that spread outward like waves across a pond? These are the types of questions that bring us closer to understanding not only the Crab Nebula but also the fundamental laws of physics that govern the cosmos. One intriguing aspect of the Crab Nebula is its contribution to our understanding of the life cycle of stars. The supernova explosion that led to the nebula's formation was the death throes of a massive star, one that had exhausted its nuclear fuel and was no longer able to support itself against the force of gravity. This collapse triggered the explosion that expelled the outer layers of the star into space, creating the nebula we see today. But what happens after the supernova? What becomes of the material that was once part of the star? In the case of the Crab Nebula, that material has formed a stunning, intricate web of gas and dust, which is constantly expanding outward. This explosion also left behind the neutron star that is now the pulsar at the center of the nebula. The extreme conditions within this neutron star are unlike anything we experience on Earth. The density of the pulsar is such that a single teaspoon of its material would weigh as much as the entire human population combined. This gives us a glimpse into the incredibly dense environments that exist in the universe, and studying these environments helps us understand how matter behaves under extreme pressure. The Crab Nebula is also crucial to understanding the process of nucleosynthesis, the creation of new elements in the aftermath of a supernova. As the explosion disperses the outer layers of the star, heavy elements like iron, nickel, and oxygen are scattered throughout space. These elements are the building blocks for future stars and planets, contributing to the ongoing cycle of cosmic evolution. The Crab Nebula, with its rich collection of elements, provides a living example of how stars are born, live, and die, and how the death of a star can lead to the creation of new worlds. The study of the Crab Nebula also plays a role in understanding how supernova remnants like it interact with the surrounding interstellar medium. The material expelled by the supernova travels outward at incredible speeds, colliding with the gas and dust in the surrounding space. These interactions create shockwaves that heat the surrounding material to temperatures of millions of degrees. The shockwaves also accelerate particles to high energies, producing the cosmic rays that we detect as high-energy radiation. By studying these shockwaves and their effects on the surrounding material, scientists can learn more about how supernova remnants influence their environment and contribute to the evolution of galaxies. Even the Crab Nebula's position in space adds to its significance. Located around 6,500 light-years from Earth, it's relatively close in cosmic terms. This proximity allows astronomers to study it in remarkable detail, using both ground-based telescopes and space-based observatories. Over the years, our understanding of the Crab Nebula has grown exponentially, thanks in large part to the availability of more advanced observational tools and techniques. With each new piece of data, we uncover new layers of complexity within the nebula, and our picture of the universe becomes that much clearer. As we continue to study the Crab Nebula, one thing is clear: we are witnessing the aftermath of an event that fundamentally reshaped the universe. The supernova that created the nebula was a spectacular, cataclysmic event that released vast amounts of energy and scattered heavy elements into space. These elements would eventually go on to form new stars, planets, and even life itself. The pulsar at the center of the nebula continues to radiate energy, offering a glimpse into the extreme physics of neutron stars. The nebula itself serves as a cosmic recycling center, where the remnants of a dead star are slowly being repurposed to form the building blocks of new cosmic structures. In this way, the Crab Nebula is not just a relic of the past but a dynamic, ever-changing part of the cosmos. It is a testament to the immense forces at work in the universe, and it continues to inspire scientists, astronomers, and curious minds alike. As we learn more about this extraordinary supernova remnant, we are reminded of the incredible power and beauty of the universe and the profound mysteries that remain just beyond our reach. With every new discovery we make about the Crab Nebula, we move closer to unraveling the secrets of the universe. The pulsar at the center of the nebula, the shockwaves that propagate through the surrounding material, and the cosmic rays that radiate outward all provide valuable clues about the processes that govern the cosmos. By studying these phenomena, we hope to one day answer some of the most fundamental questions about the nature of matter, energy, and the universe itself. The Crab Nebula will remain an object of fascination and study for generations to come. Its pulsar, with its enigmatic behavior and extreme conditions, will continue to challenge our understanding of the universe. The supernova that created it will always serve as a reminder of the incredible power and violence of the cosmos, and of the continuous cycle of creation and destruction that shapes the universe. And so, the legacy of the Crab Nebula endures. It remains one of the most important objects in the study of high-energy astrophysics, and its mysteries are far from solved. As we continue to observe, analyze, and model its behavior, we will undoubtedly uncover new insights into the workings of the universe. The Crab Nebula is not just a piece of cosmic history, it is an ongoing story, one that continues to captivate and inspire as we reach ever further into the depths of space. As we venture deeper into the enigma of the Crab Nebula, we can't help but marvel at the interplay of phenomena that are simultaneously beautiful and chaotic. The nebula's structure, as intricate as it is, represents the culmination of centuries of cosmic evolution, a powerful reminder of how a single event in the life of a star can shape the future of the universe in ways we can barely begin to understand. The material ejected during the supernova explosion has created a swirling, turbulent landscape of gas, dust, and energetic particles. This cosmic aftermath has been expanding ever since the explosion, traveling outward at tremendous speeds, around 1,500 kilometers per second. This ongoing expansion is a testament to the sheer violence of the explosion, but it also provides astronomers with a unique opportunity to study the physics of an expanding nebula. The dense, glowing filaments within the Crab Nebula act as tracers, allowing scientists to map the movement of particles and the interaction of the nebula's material with the surrounding interstellar medium. Interestingly, the Crab Nebula's expansion isn't uniform. Some regions are expanding faster than others, and these differences provide clues about the forces at play within the nebula. For example, the inner regions, closer to the pulsar, are moving faster than the outer regions. This is likely due to the pulsar's intense radiation and its powerful wind of charged particles, which influence the surrounding gas and dust. Understanding these variations in expansion speed helps scientists better model the dynamics of supernova remnants and their evolution over time. While the expansion of the nebula is a dramatic and exciting aspect of its study, it's not the only remarkable feature of this object. The Crab Nebula also represents an astonishing example of how a dying star can influence its environment in ways that extend far beyond its own death. The nebula is rich in heavy elements, many of the same elements that make up planets, stars, and even life on Earth. These elements were formed in the heart of the dying star during its lifetime, and the supernova explosion that followed scattered them across the galaxy, enriching the interstellar medium with the building blocks for new stars and planets. Through the study of these elements, scientists have been able to gain valuable insights into the processes of nucleosynthesis, the formation of the elements in the cores of stars. The Crab Nebula's supernova provides a unique opportunity to observe this process firsthand. The heavy elements that were created in the star's final moments will eventually be incorporated into the next generation of stars, continuing the cycle of cosmic evolution. The pulsar's role in this cycle is equally fascinating. As a neutron star, it is the remnant of a star that was once much larger, a massive celestial object that collapsed under its own gravity. The collapse was so intense that it created a superdense object, composed almost entirely of neutrons. The pulsar's extremely strong magnetic field and rapid rotation make it one of the most extraordinary objects in the universe. These characteristics cause the pulsar to emit beams of radiation that sweep through space, sending powerful bursts of energy across vast distances. The Crab Nebula's pulsar is one of the most studied in the universe because of its unique behavior. Its rapid rotation generates intense electromagnetic fields, which in turn accelerate particles to nearly the speed of light. These high-energy particles emit radiation that spans a broad spectrum, from radio waves to X-rays. The pulsar's constant emissions are one of the primary reasons the Crab Nebula is such a valuable object for astronomers studying high-energy astrophysics. But what's particularly fascinating is the pulsar's potential to act as a cosmic laboratory for understanding the behavior of matter under extreme conditions. Neutron stars are the densest objects in the universe, and their study helps scientists explore the behavior of matter at densities far beyond what we can replicate on Earth. The Crab Nebula's pulsar provides us with a rare opportunity to investigate the physical laws that govern such exotic environments. For instance, the study of the pulsar's emission patterns could give us insights into the behavior of matter in extreme magnetic fields or in the presence of intense gravitational forces. In addition to its role as a high-energy laboratory, the Crab Nebula's pulsar is also of great interest because it is a prime example of a rotating neutron star. As the pulsar spins, it generates a powerful wind of particles, composed mostly of electrons and positrons, that flows outward from the star. This wind is responsible for much of the nebula's bright emission, as the particles in the wind interact with the surrounding material, producing radiation across the entire electromagnetic spectrum. The pulsar's wind is also responsible for accelerating cosmic rays, which are among the most energetic particles in the universe. The study of cosmic rays is a field of great interest to astrophysicists, and the Crab Nebula's pulsar provides one of the best sources for studying them. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. They originate from a variety of sources, including supernova remnants, black holes, and active galactic nuclei. When these cosmic rays collide with the atoms in Earth's atmosphere, they produce a cascade of secondary particles, some of which reach the surface and can be detected by ground-based telescopes. By studying the cosmic rays emitted by the Crab Nebula's pulsar, astronomers can learn more about the sources of these particles, as well as the mechanisms that accelerate them to such high energies. This research has implications not only for our understanding of the Crab Nebula but also for the study of high-energy astrophysics as a whole. The pulsar's wind is one of the most powerful cosmic particle accelerators in the universe, and understanding how it works could unlock new insights into the processes that drive the most energetic phenomena in the cosmos. But the Crab Nebula's influence extends far beyond the realm of high-energy astrophysics. The nebula has also contributed to our understanding of the cosmic distance scale. The Crab Nebula is relatively nearby, located about 6,500 light-years from Earth, making it one of the closest supernova remnants to our planet. Its proximity allows astronomers to measure its expansion and map its structure in incredible detail. This has been invaluable for refining our methods for measuring the distances to other celestial objects, particularly supernova remnants, and other high-energy sources. Furthermore, the study of the Crab Nebula has played a crucial role in the development of new technologies and observational techniques. Over the years, advances in telescope technology have allowed astronomers to observe the nebula in unprecedented detail. Instruments like the Hubble Space Telescope and the Chandra X-ray Observatory have provided stunning images of the nebula, revealing intricate structures and intricate filaments of gas and dust. These observations have provided new insights into the processes that govern supernova remnants, and have helped refine our models of stellar evolution and the formation of neutron stars. As we continue to observe and study the Crab Nebula, we realize that it holds an immense wealth of information waiting to be unlocked. Every new observation adds another piece to the puzzle of understanding the forces that shape the universe. The Crab Nebula serves as a reminder of how much there is still to discover in the cosmos, and how each new piece of knowledge brings us one step closer to understanding the intricate and beautiful machinery of the universe. With each passing year, our understanding of the Crab Nebula continues to grow. The pulsar at its heart remains one of the most important sources of high-energy radiation, providing valuable clues about the fundamental forces at play in the universe. The nebula's intricate structure, shaped by the explosion of a dying star, continues to captivate astronomers and astrophysicists alike. And as we develop new technologies and observation techniques, we can only imagine the new discoveries that lie ahead. The Crab Nebula will undoubtedly remain a key focus of scientific research for years to come. It offers a wealth of opportunities to study the extremes of the universe, from the behavior of matter in intense gravitational and magnetic fields to the processes of stellar death and rebirth. As we continue to unlock the mysteries of this remarkable object, we will gain a deeper understanding of the universe and our place within it. The Crab Nebula is not just a supernova remnant. It is a cosmic laboratory, a celestial mystery, and a symbol of the infinite possibilities that await us as we explore the vast reaches of space. The Crab Nebula's role as a beacon for scientific discovery is far from over. As technology advances, so too does our ability to study the complex interactions within this fascinating remnant. Instruments like the Event Horizon Telescope, which captures images of black holes, and next-generation space telescopes, such as the James Webb Space Telescope, will soon allow astronomers to explore the nebula in even more detail. These developments are poised to answer questions that have lingered for decades and to unlock mysteries that may be even more profound than what we have already discovered. One of the areas where future research could shed light is the precise nature of the Crab Nebula's pulsar. Despite being studied for over a century, the behavior of pulsars remains a field rich with questions. How do they form such powerful magnetic fields, and how can these fields remain stable for so long? What drives the intense radiation emitted by pulsars, and how does the energy transfer through the surrounding nebula? The Crab Nebula's pulsar, with its rapid rotation and extreme magnetic field, serves as an ideal laboratory for studying these processes. Even more intriguing is the possibility that the Crab Nebula may harbor more secrets. For instance, some researchers believe that the pulsar at the nebula's heart may not be a traditional neutron star, but rather a more exotic form of compact object known as a quark star. These stars, if they exist, would be composed of quarks, fundamental particles that make up protons and neutrons. The idea of a quark star pushes the boundaries of our understanding of matter at extreme densities. If the Crab Nebula's pulsar were proven to be a quark star, it could open up an entirely new branch of astrophysics, providing answers to some of the universe's most fundamental questions about matter, gravity, and the forces that govern the cosmos. The study of the Crab Nebula is also providing valuable insights into the evolution of stars and their deaths. When a massive star explodes in a supernova, it doesn't just end its life, it catalyzes the formation of new stars and planets. The materials ejected during the explosion enrich the surrounding interstellar medium with elements like carbon, oxygen, and iron, which are essential for the creation of new stars, planets, and even life itself. In this way, the Crab Nebula serves as a cosmic factory, producing the building blocks for the next generation of stars and planetary systems. While the Crab Nebula is already an exceptional object in terms of its science value, its legacy as a source of astronomical inspiration is just as important. Since its discovery, the nebula has fascinated astronomers and laypeople alike. Its vivid, intricate structure, visible in a range of wavelengths from radio waves to X-rays, captures the imagination and offers a glimpse into the life cycle of stars. The nebula also serves as a testament to the power of human curiosity. Our desire to understand the cosmos has driven us to explore objects like the Crab Nebula with an intensity that spans centuries. The Crab Nebula's influence extends beyond the realm of astrophysics and into the broader field of science. For example, the study of pulsars and supernova remnants has led to advancements in fields such as high-energy physics, quantum mechanics, and nuclear physics. By studying the behavior of particles and electromagnetic fields in extreme environments, scientists have been able to test theories and develop new models that apply not just to the cosmos, but to Earth-based phenomena as well. Moreover, the Crab Nebula also serves as a rich source of inspiration for the world of art and popular culture. Its stunning visual displays, produced by the interaction of high-energy particles and magnetic fields, have inspired countless works of art. The nebula's striking appearance, with its tendrils of glowing gas and intricate filaments, has been a source of fascination for artists and astronomers alike. Its colorful, dynamic structure is often depicted in digital artwork, photography, and even in fictional works where the cosmic mystery of the nebula is central to the plot. By sparking the imaginations of those who encounter it, the Crab Nebula continues to have an impact that extends well beyond the scientific community. Beyond its scientific and artistic significance, the Crab Nebula is also a key part of human history. Its discovery dates back to the 18th century, when the English astronomer John Bevis first observed the nebula in 1731. However, it was not until 1054, when Chinese astronomers documented a bright new star in the sky, likely the result of the supernova explosion, that the Crab Nebula gained widespread attention. This historical record is one of the earliest examples of human observation of astronomical phenomena, and it underscores the role of astronomy in shaping our understanding of the universe. The Crab Nebula's connection to human history also highlights the intersection of ancient and modern knowledge. While the nebula was first observed and catalogued long before the advent of modern telescopes and space observatories, its true nature was not fully understood until the 20th century. The development of radio telescopes, optical telescopes, and more recently space telescopes has transformed our ability to observe and interpret distant objects like the Crab Nebula. In many ways, the nebula symbolizes the progress humanity has made in understanding the cosmos. It is a reminder that our quest for knowledge is a long and ongoing journey, one that bridges the gap between the ancient and modern worlds. As we continue to observe the Crab Nebula, we are reminded of the mysteries that remain in the universe. This supernova remnant offers us a rare glimpse into the life and death of a star, as well as the powerful forces that govern the cosmos. From the pulsar at its heart to the expanding cloud of gas and dust, every element of the Crab Nebula holds clues to understanding the universe's most fundamental processes. The Crab Nebula's legacy will continue to shape the course of astrophysical research for generations to come. As new technologies emerge and our observational techniques improve, we will gain an even deeper understanding of this fascinating cosmic object. And with each discovery, we will inch closer to answering some of the most profound questions about the nature of matter, energy, and the very fabric of space and time. The Crab Nebula stands as a testament to the power of nature and the boundless potential of human inquiry. Its supernova explosion, which occurred nearly 1,000 years ago, is still reverberating through space, influencing the universe in ways that we are only beginning to understand. The pulsar at its center, with its incredible properties and mysterious behavior, continues to be a source of wonder and inspiration. And the nebula itself remains one of the most spectacular and awe-inspiring objects in the night sky, a symbol of the infinite mysteries that lie ahead for those who dare to look up. The Crab Nebula, with all its complexity and beauty, is a cosmic legacy, a remnant of a star's final moments that continues to enrich our understanding of the universe. It is not just a distant object in the sky, but a key piece in the ever-expanding puzzle of the cosmos, providing us with a wealth of information and inspiration that will shape the future of astrophysics for generations to come. The journey of discovery around the Crab Nebula and its pulsar isn't just a scientific pursuit, it's a story of wonder, exploration, and the relentless drive to understand the cosmos. The Crab Nebula has proven to be a wellspring of new information, allowing scientists to test theories, confront mysteries, and even challenge the limits of our understanding of space and time. As new theories emerge and technologies continue to evolve, our interpretation of the nebula's vast complexity becomes more refined. But what does the future hold for the Crab Nebula? What other secrets might it reveal as we deepen our exploration of this captivating cosmic remnant? One of the most promising areas of future study is the nebula's role in the wider context of supernova remnants. The Crab Nebula is a textbook example of what happens when a massive star explodes in a supernova. Its aftermath offers us a chance to learn more about the life cycle of stars and the forces at play when these massive celestial objects end their existence. The Crab Nebula represents just one stage of a supernova remnant's evolution, but each one of these remnants is unique. By comparing the Crab Nebula to other supernova remnants, astronomers can refine their models of stellar evolution, providing insights into how different kinds of stars die and how their remnants interact with the surrounding interstellar medium. The pulsar at the heart of the Crab Nebula is also a key to understanding the complex behavior of neutron stars. Pulsars are among the most fascinating objects in the universe. These rapidly rotating neutron stars emit beams of radiation that sweep across space like cosmic lighthouses. However, the Crab Nebula's pulsar stands out because of its intense energy output and the unusual nature of its emission. While most pulsars are powered by the gradual release of energy from their rotation, the Crab Nebula's pulsar seems to be continually powered by the intense magnetic fields and matter surrounding it. Some researchers speculate that this pulsar might be an example of a particularly young and energetic neutron star, which could provide us with new insights into how pulsars evolve over time. The Crab pulsar could offer crucial clues for understanding not only the mechanics of neutron stars but also the broader processes involved in stellar collapse and the creation of compact objects. Furthermore, The Crab Nebula provides an excellent laboratory for studying the interplay between particles and magnetic fields in extreme environments. The nebula's filaments are believed to be formed by the acceleration of particles to nearly the speed of light, an incredibly energetic process that produces the nebula's vivid emission across multiple wavelengths. Understanding how particles are accelerated to such high energies in the nebula could reveal much about cosmic ray production and the mechanisms at play in other astrophysical environments, such as active galactic nuclei and gamma-ray bursts. As we learn more about these processes, we may be able to explain how cosmic rays propagate through space, interact with matter, and influence the structure of galaxies. The Crab Nebula also holds the potential to further our understanding of magnetic fields, which are crucial to the formation of stars, planets, and even life itself. Magnetic fields in the nebula are thought to be extraordinarily strong, with some parts of the nebula exhibiting magnetic fields that are 1 trillion times stronger than Earth's. These fields not only play a role in shaping the nebula's structure but also influence the movement of charged particles within it. Researchers are constantly working to understand the mechanisms behind these powerful magnetic fields, how they are generated, and how they interact with the nebula's pulsar. The Crab Nebula's pulsar acts as a giant magnet, affecting the surrounding material and creating a high-energy environment that might hold clues about how magnetic fields evolve in different cosmic environments. This knowledge could also help us better understand magnetic fields in other astrophysical phenomena, such as in the cores of stars or in the vicinity of black holes. Another intriguing question that continues to fuel research into the Crab Nebula is its connection to other objects in the universe. The Crab Nebula's pulsar is one of the most well-known and well-studied examples of a rapidly rotating neutron star, but it's not the only one. There are other neutron stars and pulsars throughout the universe that could provide valuable comparisons. The study of these objects could lead to the identification of commonalities between them, which in turn would help scientists develop a more complete picture of how such objects form and evolve. By investigating a range of pulsars and supernova remnants, astronomers could test the limits of current theories and refine our models of stellar collapse and neutron star formation. The Crab Nebula's unique combination of characteristics makes it an ideal candidate for future comparison, as its pulsar remains one of the most powerful examples in the universe. Beyond the scientific frontiers, the Crab Nebula will likely continue to capture the imagination of those interested in space and the mysteries it holds. The nebula's striking beauty and its enigmatic features have inspired countless stories, artworks, and scientific endeavors. Its prominence in popular culture further strengthens the nebula's position as one of the most iconic astronomical objects in history. As more people become fascinated by the universe, the Crab Nebula's legacy will continue to grow, sparking further public interest in science and space exploration. Its captivating appearance, combined with the profound mysteries it holds, ensures that it will remain a symbol of cosmic curiosity and scientific inquiry. In the coming decades, the Crab Nebula will undoubtedly continue to be an essential part of the astronomical community's efforts to explore the universe. The advancement of observational tools and techniques, such as the upcoming space telescopes and ground-based observatories, will allow us to study this supernova remnant in even greater detail. The high-resolution imaging and spectroscopy techniques of the future will undoubtedly reveal more about the complex interactions taking place within the nebula, shedding light on the forces that shape the universe. It's possible that future generations of scientists will make groundbreaking discoveries that further enrich our understanding of the Crab Nebula, revealing even more about its origins, its pulsar, and its ongoing evolution. One of the most exciting possibilities is the potential discovery of new objects and phenomena within the nebula. As we peer deeper into the heart of the Crab Nebula, we may uncover features that have remained hidden for centuries. These could include previously undetected remnants of the original supernova explosion, strange interactions between the pulsar and its environment, or even the presence of exotic particles and fields that have yet to be discovered. As our knowledge of the universe expands, so too will our ability to make sense of these discoveries, adding yet another layer of understanding to this already fascinating object. But perhaps the most profound realization that comes with studying the Crab Nebula is its reminder of the vastness and complexity of the universe. Despite being located over 6,500 light-years away, the Crab Nebula offers us a glimpse into the forces and processes that govern the cosmos. It allows us to study the life and death of stars, the formation of compact objects, and the behavior of matter under extreme conditions. Through the study of this supernova remnant, we are able to probe the deepest questions about the nature of existence, time, and space itself. In this way, the Crab Nebula is not just a remnant of a star's death, but a living laboratory, a place where the universe's most profound mysteries are still being unraveled. As we continue to investigate this cosmic relic, the Crab Nebula will undoubtedly continue to surprise and enlighten us, offering new insights into the workings of the universe and challenging our understanding of the fundamental forces that shape reality. Its legacy as a supernova remnant is far from over. The secrets it holds will keep astronomers and scientists captivated for generations to come. The Crab Nebula continues to be a prime example of how science and exploration converge in the quest to understand the universe. As our tools improve and our understanding of the cosmos deepens, new theories and observations will allow us to uncover even more layers of complexity within this remarkable object. One area that is ripe for future exploration is the detailed study of the Crab Nebula's magnetic fields. Magnetic fields are a fundamental aspect of cosmic phenomena, playing a significant role in everything from the formation of stars to the behavior of galaxies. The magnetic fields within the Crab Nebula are particularly fascinating because of their strength and how they interact with the pulsar at the center. Magnetic fields are generated by the movement of charged particles, and in the case of the Crab Nebula, these fields are tied directly to the pulsar. As the pulsar emits its intense beams of radiation, the surrounding space is filled with a highly energetic plasma that interacts with the magnetic fields, accelerating particles to speeds close to the speed of light. This process, known as particle acceleration, results in the high-energy particles that are responsible for the Crab Nebula's dazzling emission across multiple wavelengths. These particles travel outward from the pulsar, creating the nebula's filaments and glowing rings. Understanding how these particles are accelerated and how they interact with the magnetic fields of the nebula could provide us with important insights into similar processes occurring throughout the universe. Another important aspect of the Crab Nebula's magnetic fields is their role in the nebula's overall structure. The nebula is not a static, unchanging object. It is a dynamic system that is constantly evolving. The interactions between the pulsar's radiation, the particles in the nebula, and the magnetic fields cause the nebula to expand and evolve over time. This makes the Crab Nebula an incredibly useful laboratory for studying the long-term dynamics of supernova remnants and their interaction with the surrounding interstellar medium. By continuing to study the Crab Nebula, astronomers can develop more accurate models for how these types of remnants evolve over time and how they affect the broader cosmic environment. One of the most exciting possibilities for future research in the Crab Nebula is the potential discovery of new forms of high-energy radiation. While much of the nebula's energy is emitted in the form of X-rays and gamma rays, scientists are still exploring the possibility of discovering new, previously unobserved types of radiation. With the development of more advanced space telescopes and observational instruments, we may soon be able to detect radiation across even more wavelengths, providing us with a more complete picture of the nebula's activity. This could include the discovery of rare cosmic phenomena, such as exotic particles or unknown forms of energy, that could further challenge our understanding of the universe. The pulsar at the center of the Crab Nebula will continue to be a key subject of study in the coming years. As the pulsar spins rapidly, emitting a regular pulse of radiation, it provides a valuable window into the behavior of neutron stars. Neutron stars are some of the densest objects in the universe, formed when massive stars collapse at the end of their life cycles. The Crab pulsar, with its immense power and unique properties, offers an opportunity to study the behavior of these exotic objects in unprecedented detail. In particular, researchers are keen to learn more about the pulsar's magnetic field and how it is able to generate such intense radiation. The pulsar's activity also provides a fascinating glimpse into the life cycle of neutron stars and how they change over time. Understanding these changes could reveal crucial information about the nature of neutron stars, helping to refine our models of stellar evolution. At the same time, The Crab Nebula is also an important tool for studying the broader processes of supernova explosions and the formation of supernova remnants. Supernovae are some of the most violent and energetic events in the universe, and studying the aftermath of these explosions provides us with key insights into the life and death of stars. The Crab Nebula is one of the best examples of a supernova remnant, offering astronomers a unique opportunity to observe the consequences of a star's death and the complex processes that unfold in the aftermath. The nebula's intricate structure, with its filaments and pulsar, provides valuable clues about the physical mechanisms at play in the explosion and how the surrounding material is shaped by the intense energy released during the event. As our understanding of supernovae improves, the Crab Nebula will continue to serve as a crucial reference point, helping to refine our models of stellar collapse and the creation of neutron stars. Perhaps one of the most profound implications of studying the Crab Nebula is the way it helps to frame our understanding of the universe as a whole. The Crab Nebula is a physical manifestation of cosmic processes that occur on a scale far beyond anything we experience on Earth. It serves as a reminder of the vastness of the cosmos and the incredible forces at work in the universe. When we study the Crab Nebula, we are not just learning about a single supernova remnant. We are gaining insights into the fundamental workings of the universe itself. The nebula's pulsar, magnetic fields, and particle accelerators offer a window into the dynamic processes that shape stars, galaxies, and the very fabric of space and time. Through the study of such objects, we come to appreciate the complexity and interconnectedness of the universe, helping us better understand our place within it. As the years pass, the Crab Nebula will continue to be a source of inspiration and discovery for astronomers, scientists, and the general public alike. With each new breakthrough, we move one step closer to unraveling the many mysteries that lie at the heart of this cosmic relic. The Crab Nebula's pulsar, magnetic fields, and intricate structure will continue to captivate us, providing endless opportunities for exploration and discovery. Whether through the advancement of observational technology or the development of new scientific theories, the Crab Nebula will remain one of the most important objects in the study of astrophysics and a testament to the wonders of the universe. Looking forward, one can only imagine the new frontiers we will explore in the study of the Crab Nebula. As technology continues to evolve, we may uncover even more surprises within its glowing filaments and the surrounding cosmic environment. We may discover new phenomena that challenge our current understanding of physics, opening up new realms of knowledge that we have yet to explore. The Crab Nebula, with its pulsar at the center and its complex network of magnetic fields and energetic particles, holds a wealth of information that continues to elude our grasp. Yet, each new discovery brings us closer to unraveling its secrets, and as we continue to study this enigmatic supernova remnant, we are reminded of the vastness and mystery of the universe we live in. The Crab Nebula will forever stand as a symbol of the infinite possibilities that await us in our quest to understand the cosmos. With each passing year, we uncover new insights, pushing the boundaries of what we know about the universe and our place within it. Whether it's the discovery of new forms of radiation, the study of pulsar dynamics, or the exploration of the nebula's intricate structure, the Crab Nebula's legacy as a scientific treasure trove will continue to inspire future generations of astronomers, scientists, and dreamers alike. As we continue to look deeper into the Crab Nebula and its captivating features, one of the most intriguing aspects remains the ongoing mystery of its age and how it evolves. When astronomers first observed the Crab Nebula, they learned that the supernova explosion responsible for its creation occurred in the year 1054. As recorded by various cultures at the time. Over the centuries, the Crab Nebula has been slowly expanding, and understanding its rate of expansion is crucial to figuring out how long it will continue to evolve. The rate of expansion of a supernova remnant like the Crab Nebula is influenced by a variety of factors, including the density of the surrounding interstellar medium and the energy released by the pulsar at the center. As the nebula expands, the shockwave created by the explosion interacts with the surrounding material, compressing it and creating new regions of higher density. These interactions play a significant role in shaping the nebula's structure and contribute to the complex network of filaments and rings that we observe today. The pulsar's wind, which consists of high-energy particles streaming out from the pulsar at speeds approaching the speed of light, also contributes to the nebula's ongoing evolution. This wind is responsible for compressing and energizing the material within the nebula, further enhancing the intricate structure that makes the Crab Nebula so visually striking. The expansion of the Crab Nebula also affects the dynamics of the surrounding region of space. Over time, the supernova remnant will continue to disperse the material from the original star, enriching the surrounding interstellar medium with heavy elements that were created during the explosion. These elements, such as oxygen, carbon, and nitrogen, play an important role in the creation of new stars and planetary systems. In this way, the Crab Nebula is not just a relic of the past, it is also a source of material that will be incorporated into future generations of stars, planets, and other celestial objects. This ongoing process of material recycling is a key component of the life cycle of stars and contributes to the ever-changing nature of the universe. While the expansion of the Crab Nebula is a relatively slow process, it is still occurring at a significant rate. Observations from telescopes such as Hubble and Chandra have shown that the nebula is expanding by about 1,500 kilometers per second. This might seem fast on the scale of human experience, but in the context of the vast distances involved in space, it's actually a slow process. Despite this, the nebula's expansion is still noticeable, and scientists continue to monitor its growth to better understand how supernova remnants evolve over time. Interestingly, the Crab Nebula's expansion is not uniform. The structure of the nebula is highly irregular, with certain regions expanding more rapidly than others. This is due to the complex interactions between the pulsar wind, the shockwave from the supernova explosion, and the surrounding interstellar medium. In some regions, the material is compressed by the shockwave, leading to faster expansion, while in other areas, the material is stretched out, resulting in slower expansion. These variations in the expansion rate contribute to the nebula's intricate and uneven appearance, with filaments and structures that seem to glow with an almost otherworldly energy. One of the most remarkable features of the Crab Nebula is its pulsar, which continues to provide valuable insights into the behavior of neutron stars. The pulsar at the center of the nebula is not just a source of light, it is also a powerful generator of energy. As the pulsar spins, it emits a steady stream of electromagnetic radiation across a wide range of wavelengths, from radio waves to gamma rays. This radiation is a result of the intense magnetic fields around the pulsar, which accelerate charged particles to incredibly high speeds. As these particles travel through the surrounding nebula, they interact with the material, creating the stunning light displays that make the Crab Nebula so visually captivating. The pulsar's activity also provides valuable information about the nature of neutron stars and how they behave. Neutron stars are the remnants of massive stars that have exploded in supernovae, and they are incredibly dense objects. A neutron star's density is so high that it contains more mass than the Sun, but it is compressed into a sphere just a few kilometers across. The gravitational forces inside a neutron star are so strong that they crush atoms into neutrons, creating a unique state of matter that cannot be replicated elsewhere in the universe. The behavior of the pulsar at the heart of the Crab Nebula is an example of how these extraordinary objects can emit vast amounts of energy and affect their surrounding environment in profound ways. As astronomers continue to study the Crab Nebula and its pulsar, they are gaining important insights into the physics of neutron stars and the extreme environments that exist around them. One of the key questions researchers are investigating is how pulsars are able to maintain their rapid rotation rates. Despite being composed of such dense material, neutron stars can spin at incredible speeds, with some pulsars rotating hundreds of times per second. This rapid rotation is a result of the conservation of angular momentum, which causes an object to spin faster as it contracts. However, scientists are still working to understand the mechanisms that allow pulsars to sustain such high rotational velocities over time. Another fascinating aspect of the pulsar at the center of the Crab Nebula is its role in the creation of the nebula's intricate structure. The pulsar emits a continuous stream of charged particles, which interact with the surrounding gas and dust, creating the filaments and rings that we observe. These particles are accelerated to extremely high energies by the pulsar's magnetic fields, and as they travel through the nebula, they emit radiation in the form of light and other types of electromagnetic waves. This interaction between the pulsar's wind and the material in the nebula is responsible for the nebula's stunning appearance and its continuous evolution. Over time, the energy from the pulsar has shaped the nebula into the complex structure we see today, and it will continue to play a central role in the nebula's future development. One of the most compelling reasons to continue studying the Crab Nebula is the potential it holds for advancing our understanding of astrophysical processes. By studying this supernova remnant and its pulsar, we can learn more about the behavior of neutron stars, the dynamics of supernova explosions, and the ways in which cosmic materials interact across vast distances. The Crab Nebula serves as a unique laboratory for studying these processes in real time, providing a wealth of data that will continue to inform our understanding of the universe for generations to come. As we continue to develop new tools and technologies, the Crab Nebula will undoubtedly reveal even more secrets, offering new insights into the fundamental workings of the cosmos. Looking beyond the Crab Nebula, we can see the broader implications of studying supernova remnants. Supernovae are not just isolated events. They are integral to the evolution of galaxies and the formation of new stars. The materials created in supernova explosions, including heavy elements such as carbon, oxygen, and iron, are essential for the formation of planets and life as we know it. By studying the Crab Nebula, we are not just learning about the death of a single star. We are gaining insights into the processes that shape the very fabric of the universe. Supernova remnants like the Crab Nebula play a crucial role in the recycling of matter in the universe, enriching the interstellar medium with the elements that are necessary for the formation of new stars and planetary systems. The Crab Nebula also offers us a glimpse into the far future. As the nebula continues to expand and evolve, it will eventually disperse into the surrounding space, leaving behind only the pulsar at its center. This process will take thousands of years, but in the grand scheme of the universe, it is just a blip in time. The material from the Crab Nebula will eventually be incorporated into other cosmic structures, contributing to the creation of new stars and planets. In this way, the legacy of the Crab Nebula will live on, continuing to shape the universe long after its visible remnants have faded from view. The Crab Nebula serves as a powerful reminder of the dynamic and ever-changing nature of the cosmos. From its dramatic origin in a supernova explosion to its ongoing evolution driven by the pulsar at its center, the Crab Nebula is a symbol of the beauty and complexity of the universe. Its study continues to provide us with valuable insights into the fundamental processes that govern the behavior of stars, galaxies, and the very fabric of space itself. As we continue to explore this remarkable object, we will undoubtedly unlock even more mysteries, expanding our knowledge and deepening our appreciation of the vast and awe-inspiring universe that we call home. As we delve deeper into the Crab Nebula's significance, it's important to explore how it fits into the larger context of cosmic evolution. The Crab Nebula is a prime example of a supernova remnant, and studying it provides scientists with a deeper understanding of the life cycle of stars. The remnants of such supernovae are not only fascinating in their own right but are also key to understanding the mechanisms that drive the evolution of galaxies. In this way, the Crab Nebula is part of a much larger cosmic process that has implications for the entire universe. Supernova remnants like the Crab Nebula are instrumental in enriching the interstellar medium with heavy elements. These elements, formed in the hearts of dying stars, are essential for the creation of new stars and planets. Without these elements, the universe would be a very different place, devoid of the complexity and diversity of objects that we observe today. The Crab Nebula, therefore, is a symbol of the constant recycling of matter that takes place in the cosmos. Each supernova explosion sends out a burst of elements, seeding the surrounding space with the building blocks of new celestial bodies. The Crab Nebula also offers valuable clues about the fate of other supernova remnants in our universe. While this particular remnant is relatively young at around 1,000 years old, other remnants from more ancient supernovae may have undergone different stages of evolution. By comparing the Crab Nebula to these older remnants, astronomers can gain insights into the long-term evolution of supernova remnants and better understand the forces that drive their transformation. The study of these remnants helps scientists to better comprehend the complex interactions between stellar death, galactic evolution, and the formation of new stars and planets. In addition to the role that the Crab Nebula plays in the cosmic cycle of birth and death, it also provides a unique laboratory for testing our understanding of the fundamental laws of physics. The pulsar at the center of the Crab Nebula, with its extreme environment and bizarre behavior, offers an opportunity to test theories related to the behavior of matter under extreme conditions. For example, the dense core of the neutron star at the heart of the Crab Nebula is a natural laboratory for studying the physics of neutron-rich matter. This type of matter, which exists only in the cores of neutron stars, behaves in ways that are fundamentally different from the matter we encounter on Earth. The Crab Nebula's pulsar also challenges our understanding of magnetism and radiation. The magnetic fields surrounding the pulsar are extremely powerful, and they accelerate particles to nearly the speed of light. These high-energy particles interact with the surrounding material in the nebula, creating a variety of radiation, including X-rays and gamma rays. The study of these interactions helps astronomers to probe the nature of these extreme magnetic fields and better understand how they influence the behavior of matter at these unprecedented energy levels. Moreover, the study of the Crab Nebula allows astronomers to explore the properties of relativistic jets, which are streams of particles moving at speeds close to the speed of light. These jets are a common feature of many astrophysical objects, including black holes and pulsars, but they are most prominently displayed in the Crab Nebula. The pulsar at the center of the nebula emits two distinct jets of particles that move in opposite directions, creating an awe-inspiring sight that has been captured in incredible detail by various space telescopes. These jets are a critical component of the nebula's overall structure and play a major role in its ongoing evolution. By studying the jets of the Crab Nebula, scientists can better understand how similar phenomena occur in other parts of the universe. One particularly intriguing aspect of the Crab Nebula is its role in the study of cosmic ray acceleration. Cosmic rays are high-energy particles that travel through space and impact Earth's atmosphere, where they can produce a variety of interesting phenomena. It's believed that the Crab Nebula is one of the primary sources of cosmic rays in our galaxy, and studying the nebula's pulsar and the particles it emits provides astronomers with crucial information about how these high-energy particles are generated and accelerated. This information is important for understanding the broader cosmic environment, and could have implications for space weather and the protection of astronauts in future space missions. The Crab Nebula's pulsar is also a source of intense electromagnetic radiation across a wide range of wavelengths, from radio waves to X-rays. This radiation is a result of the pulsar's magnetic fields, which accelerate charged particles to extraordinary speeds. The electromagnetic radiation emitted by the pulsar is not just a byproduct of its activity. It is a direct reflection of the complex physical processes taking place in the nebula. By studying this radiation, scientists can gain deeper insights into the physics of pulsars and neutron stars, which are some of the most enigmatic objects in the universe. The Crab Nebula serves as a natural laboratory for understanding the nature of high-energy astrophysical phenomena. The study of the Crab Nebula has also led to important advances in our understanding of time and space. The pulsar at the center of the nebula is a highly reliable cosmic clock, with its precise rotation providing valuable data for testing theories of relativity and the behavior of matter in extreme gravitational fields. Scientists have been able to use the pulsar's rotation to make measurements of time with incredible accuracy, helping to refine our understanding of the fabric of spacetime itself. This is just one example of how the study of supernova remnants like the Crab Nebula can push the boundaries of our knowledge and help us to better understand the fundamental nature of the universe. The Crab Nebula also serves as a reminder of the remarkable capabilities of modern astronomy. The ability to observe and study objects like the Crab Nebula in such detail is a testament to the incredible advancements in technology that have taken place over the past few decades. Telescopes like the Hubble Space Telescope, the Chandra X-ray Observatory, and the Very Large Telescope have provided us with stunning images of the nebula, revealing its complex structure and intricate details. These observations have opened up new avenues of research and have greatly expanded our understanding of the cosmos. Looking ahead, the Crab Nebula will continue to be a focal point for research in astrophysics and cosmology. With the advent of next-generation telescopes and observational techniques, scientists will be able to explore the nebula in even greater detail, unlocking new insights into its evolution and the behavior of the pulsar at its center. The Crab Nebula offers a glimpse into the future of astronomical research, where the study of supernova remnants, neutron stars, and other extreme objects will continue to provide valuable clues about the nature of the universe and the fundamental forces that govern it. As we continue to study the Crab Nebula and its pulsar, we are reminded of the dynamic and ever-evolving nature of the cosmos. The Crab Nebula is not just a relic of a long-dead star, it is a living, evolving object that continues to shape the universe in profound ways. Its study has led to significant advances in our understanding of the universe, and it will undoubtedly continue to be a source of discovery for years to come. In the grand scheme of the cosmos, the Crab Nebula is just one small piece of the puzzle, but it is a piece that offers us a window into some of the most fundamental processes that drive the universe. Ultimately, the Crab Nebula is a symbol of the incredible complexity and beauty of the universe. From its dramatic creation in a supernova explosion to its ongoing evolution driven by the pulsar at its center, the Crab Nebula is a testament to the power and mystery of the cosmos. It continues to challenge our understanding of the laws of physics and inspires us to reach further into the unknown. The study of the Crab Nebula is far from over, and as we continue to unlock its secrets, we will gain a deeper appreciation for the vastness and wonder of the universe. As we push the boundaries of our understanding, the Crab Nebula continues to captivate scientists, astronomers, and curious minds alike. The richness of its features and the complexity of its behavior make it a perfect case study in the cosmos, where death and rebirth, destruction and creation, coexist in a dynamic, awe-inspiring dance. While we've explored its creation, its structure, its pulsar, and the role it plays in cosmic evolution, there are still so many aspects of the Crab Nebula to be uncovered. In fact, it's not just the physical properties that intrigue us, but also the deeper questions about how these celestial phenomena influence the very fabric of the universe. Let's consider the immense power of the Crab Nebula's pulsar in greater detail. Pulsars are fascinating by nature, as they challenge our understanding of matter and energy. The Crab Nebula's pulsar, known as PSRB 0531+21, is one of the most intensely studied pulsars in the universe. It's spinning at an incredible rate of 30 times per second, making it an extremely fast and highly regular clock in the sky. This rapid spinning, coupled with its powerful magnetic field, accelerates particles to nearly the speed of light, producing a consistent and focused beam of electromagnetic radiation. The pulsar acts almost like a lighthouse in space, with its energy being emitted in precise pulses that can be detected across vast distances. What makes the Crab Nebula's pulsar so intriguing is not just its regularity or intensity, but its ability to produce such a wide range of radiation across the electromagnetic spectrum. From radio waves to X-rays to gamma rays, the Crab Nebula's pulsar emits a tremendous variety of radiation, each revealing different aspects of the physical processes occurring within and around the pulsar. This immense energy output is part of what makes the Crab Nebula a unique and invaluable subject of study. To fully appreciate the scale of this phenomenon, it's crucial to understand the underlying physics. The energy produced by the Crab Nebula's pulsar is not like the energy we encounter on Earth. Here, on our home planet, energy is often a result of chemical reactions or the conversion of mass to energy in nuclear processes. However, in the case of the pulsar, the energy is a direct result of the collapse of a massive star. The intense gravitational forces at play during this collapse cause the star's core to become a neutron star, a type of dense, compact object made almost entirely of neutrons. The energy released during this collapse is so great that it propels the neutron star to spin rapidly, and the magnetic field generated by this spinning creates the energetic particles that give rise to the radiation we detect from the nebula. But this is just the tip of the iceberg when it comes to understanding the Crab Nebula. The interaction between the pulsar's magnetic fields and the surrounding material, including the remnants of the supernova explosion, results in a complex web of electromagnetic radiation. These interactions are not only key to understanding the pulsar itself but also offer clues about how matter behaves under extreme conditions that cannot be replicated in laboratories on Earth. By studying these interactions, scientists are pushing the limits of our understanding of electromagnetism, quantum mechanics, and the fundamental forces that govern the universe. One of the most exciting aspects of studying the Crab Nebula is its potential to answer some of the most fundamental questions in astrophysics. How do the most extreme objects in the universe behave? What forces govern their evolution? How do magnetic fields interact with matter in ways that lead to the creation of high-energy particles and radiation? The Crab Nebula, with its intense radiation and pulsar at the center, is providing answers to these questions and giving scientists new insights into the nature of matter and energy in some of the most extreme environments in the universe. The Crab Nebula also plays a critical role in our understanding of supernovae and their aftermath. Supernovae are one of the most powerful events in the universe, capable of releasing energy that outshines an entire galaxy. When a massive star reaches the end of its life and undergoes a supernova explosion, the result is a violent release of energy and the ejection of vast amounts of matter into space. What happens next? The Crab Nebula is an excellent example of what happens after the explosion. The nebula is the result of the outward expansion of the material expelled by the supernova, and it continues to expand and evolve over time. By studying this remnant, we gain insight into the fate of stars after they die and the processes that take place as their material is scattered throughout the universe. These supernova remnants, such as the Crab Nebula, are important not only for their role in cosmic evolution but also for their role in enriching the interstellar medium with heavier elements. As these supernova remnants cool and evolve, they begin to produce and disperse elements that are essential for the formation of new stars, planets, and even life. The Crab Nebula, like other supernova remnants, acts as a cosmic recycling center, transforming the energy and matter from a once dying star into the raw materials needed for the birth of new celestial bodies. This process of cosmic recycling is critical for the ongoing evolution of galaxies and the formation of complex structures within the universe. The Crab Nebula's pulsar is also an ideal place for studying the effects of relativistic jets. The pulsar at the center of the nebula produces two powerful jets of high-energy particles that are ejected at nearly the speed of light. These jets are made up of highly energetic electrons and positrons, which interact with the surrounding material, creating a variety of different emissions. These jets are a prominent feature of the Crab Nebula and are a key source of its characteristic X-ray and gamma-ray emissions. The behavior of these jets provides valuable information about the acceleration of particles in extreme environments, and their study can help scientists better understand similar phenomena that occur in other parts of the universe, such as around black holes and in active galactic nuclei. The Crab Nebula also offers a unique opportunity to study the phenomenon of cosmic ray acceleration. Cosmic rays are high-energy particles that travel through space, and they are believed to originate from powerful sources such as supernovae and active galactic nuclei. The Crab Nebula is one of the primary sources of cosmic rays in our galaxy, and by studying its pulsar and the radiation it emits, scientists can learn more about the processes that accelerate these particles to such extreme energies. This knowledge is critical not only for understanding cosmic rays but also for understanding the broader environment of the universe and the potential impacts of high-energy radiation on space exploration. Another exciting area of research related to the Crab Nebula is its potential to advance our understanding of gravitational waves. Gravitational waves are ripples in space-time caused by the acceleration of massive objects, and they carry valuable information about the most extreme events in the universe. The Crab Nebula, with its rapidly spinning pulsar and extreme gravitational forces, is a potential source of gravitational waves. By studying the nebula and its pulsar, scientists can learn more about how gravitational waves are generated and how they can be detected. This is just another example of how the Crab Nebula is not only a fascinating object in itself but also a key to unlocking some of the deepest mysteries of the universe. As we continue to observe and study the Crab Nebula, we are also learning more about the tools and technologies that allow us to explore the cosmos. The Crab Nebula has been observed in detail by a variety of telescopes, from ground-based observatories to space telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory. These tools allow scientists to study the nebula in different wavelengths of light, from radio waves to X-rays, revealing a wealth of information about the nebula's structure, composition, and behavior. As new technologies continue to emerge, the study of the Crab Nebula and other similar objects will only become more detailed and more precise, offering even more insights into the workings of the universe. The Crab Nebula is a testament to the complexity and beauty of the universe. It is a living remnant of a cataclysmic event that continues to captivate and inspire scientists, astronomers, and space enthusiasts alike. As we study the Crab Nebula, we not only learn more about this fascinating object but also about the fundamental processes that govern the cosmos. From the rapid rotation of its pulsar to the violent remnants of the supernova explosion, the Crab Nebula offers a unique window into the extreme and mysterious world of astrophysics. Its study is helping to push the boundaries of our understanding, and it will undoubtedly continue to be a key focus of research for many years to come. The Crab Nebula, as we have seen, is not just an astronomical object, it is a cosmic laboratory where some of the most extreme processes in the universe are laid bare for us to study. From the pulsar at its heart to the energetic interactions between particles and radiation, every aspect of the Crab Nebula invites us to look deeper, to question more, and to explore further into the mysteries of space. One area of continued interest within the Crab Nebula is its role as a testbed for the theory of relativity. Albert Einstein's general theory of relativity, which describes the behavior of gravity in extreme conditions, is critical to our understanding of objects like neutron stars and pulsars. The Crab Nebula's pulsar, in particular, provides a natural laboratory where we can observe relativistic effects in action. For instance, the immense gravitational pull of the neutron star at the center of the nebula causes light and radiation to bend in ways that reveal the underlying curvature of spacetime. As scientists study these phenomena, they are not only testing Einstein's theory in a new environment but also gaining new insights into how matter behaves under intense gravitational forces. Moreover, as astronomers continue to develop more advanced instruments, the potential to study the Crab Nebula in unprecedented detail increases. For instance, the next generation of space telescopes, such as the James Webb Space Telescope, JWST, could allow scientists to observe the Crab Nebula in infrared wavelengths, revealing new aspects of its structure and behavior that were previously invisible. The JWST's ability to peer through cosmic dust and observe distant objects with incredible clarity could offer breakthroughs in our understanding of the nebula's evolution. Additionally, future missions dedicated to the study of cosmic rays and gamma rays could uncover even more about the energetic particles produced by the pulsar and how they interact with the surrounding environment. In a sense, the Crab Nebula's pulsar continues to be a beacon of scientific curiosity. Its unusual properties push the limits of our knowledge and force us to rethink how we understand the most fundamental forces in the universe. From its spinning motion to its intense electromagnetic radiation, the pulsar is a cosmic engine that challenges our perceptions of space and time. Each new discovery about the pulsar adds a piece to the puzzle of understanding neutron stars, magnetic fields, and the dynamics of high-energy astrophysics. Perhaps one of the most compelling aspects of the Crab Nebula's study is the role it plays in inspiring future generations of scientists and thinkers. As we study the remnants of this ancient supernova, we are constantly reminded of the vastness and mystery of the universe. The Crab Nebula serves as a reminder of the sheer scale of the cosmos and the complexity of the phenomena that exist beyond our own world. For students and researchers alike, it presents a model for how science can continually evolve, with each new observation leading to new questions and new insights. Its enduring mystery is a call to action for anyone interested in unraveling the secrets of the universe. While we continue to learn about the Crab Nebula, its impact goes beyond just the scientific realm. It serves as a testament to the human spirit of exploration and the drive to understand our place in the universe. The Crab Nebula is a reminder that even the most violent events, like a supernova explosion, can give birth to something truly remarkable. Just as the death of a star can lead to the formation of new cosmic structures, our pursuit of knowledge can lead to new understandings and discoveries that reshape our worldview. In the broader context of the universe, the Crab Nebula's pulsar is just one of many pulsars scattered across the sky. However, its brightness and the wealth of information it provides make it an extraordinary case study. Pulsars in general have been of great interest to astronomers because they offer a window into some of the most extreme conditions that exist in the universe. They allow us to study the effects of intense magnetic fields, rapid rotation, and high-energy radiation, all of which are critical for understanding the behavior of matter and energy in extreme environments. The Crab Nebula pulsar stands as a representative example of these phenomena, providing a wealth of data that is helping us piece together the puzzle of stellar evolution, neutron star formation, and cosmic radiation. But the Crab Nebula's influence extends beyond the field of astrophysics. The study of this supernova remnant and its pulsar has implications for a wide range of scientific disciplines, from particle physics to quantum mechanics. The Crab Nebula's high-energy particles and the processes that create them provide important clues about the fundamental forces that govern the behavior of matter at the most microscopic scales. By studying these particles and the way they interact with each other, scientists are gaining new insights into the nature of the universe's most basic building blocks. This has the potential to lead to breakthroughs not only in astrophysics but also in fields such as quantum computing, high-energy particle physics, and even materials science. The Crab Nebula also holds potential for contributing to our understanding of more theoretical aspects of physics. Concepts like dark matter and dark energy, two of the greatest mysteries of modern science, might find some answers in the study of objects like the Crab Nebula. While we do not yet know how these mysterious substances influence the universe, we know that their effects can be observed through the gravitational and electromagnetic forces they exert on visible matter. By studying supernova remnants like the Crab Nebula, scientists may uncover subtle clues that could help us understand the role that dark matter and dark energy play in shaping the universe's evolution. The Crab Nebula, as a cosmic laboratory, might hold the key to solving some of the most elusive mysteries in physics today. Moreover, the Crab Nebula's role as a cosmic factory for elements cannot be overstated. Supernovae like the one that created the Crab Nebula are responsible for creating many of the elements that make up our planet, and, in turn, the life that exists on it. When a massive star explodes in a supernova, the intense heat and pressure cause the fusion of lighter elements into heavier ones. These elements are then expelled into space, where they can eventually be incorporated into new stars, planets, and even life forms. The Crab Nebula, with its rich mix of elements and ongoing evolution, is a perfect example of how the cosmos constantly recycles material to build the next generation of celestial bodies. The future of the Crab Nebula's study is an exciting one. As new technologies come online, astronomers will have more tools at their disposal to delve deeper into the mysteries of this ancient remnant. From new telescopes to advancements in computing, the next generation of scientists will have unprecedented access to the data they need to continue unraveling the secrets of the Crab Nebula and its pulsar. As we continue to observe and analyze this enigmatic object, we will no doubt uncover new layers of understanding that will push the boundaries of our knowledge even further. Ultimately, the Crab Nebula is a reminder of the ever-expanding frontier of human knowledge. It is a monument to the power of curiosity and the relentless pursuit of understanding. Its study invites us to explore the universe's deepest mysteries, to question everything we think we know, and to continue searching for answers to the fundamental questions of existence. As we stand on the shoulders of the great astronomers and physicists who have come before us, we are reminded that the quest for knowledge is a journey without end, one that will continue to inspire and captivate future generations for years to come. As we continue to look at the Crab Nebula, it's important to note how this supernova remnant helps us explore the life cycles of stars. The Crab Nebula is the aftermath of a star's death, but this death was not the end. Instead, it marks a transition into something entirely new, one of the most extreme and fascinating processes in the universe: the birth of a neutron star, a pulsar, and the creation of a nebula that remains visible across vast distances in space. This transformation shows us not only the immense power contained within stars but also the critical role they play in shaping the universe around them. A supernova explosion like the one that created the Crab Nebula is a violent event. But its violence is a necessary part of the cosmic cycle. As massive stars exhaust their nuclear fuel, they undergo a dramatic collapse, followed by an explosion that releases an enormous amount of energy. The result is a supernova, and in some cases, such as the Crab Nebula, the remnants of this explosion form complex structures that provide astronomers with unique opportunities to study the remnants of these celestial events. These remnants can reveal a wealth of information about stellar death, neutron star formation, and the broader processes of cosmic evolution. One of the fascinating aspects of the Crab Nebula is its pulsar, the rapidly rotating neutron star at its center. This pulsar, which rotates 30 times per second, acts as a cosmic lighthouse, emitting regular pulses of radiation that can be detected across vast distances. The pulsar's magnetic field is incredibly strong, generating vast amounts of energy. In fact, the Crab pulsar is one of the most powerful sources of high-energy radiation in the sky. Studying this pulsar gives us important clues about the nature of matter and energy in extreme conditions. The Crab pulsar is also a prime example of the behavior of matter in a neutron star, where the pressure is so intense that electrons and protons are crushed together to form neutrons. The radiation emitted by the pulsar interacts with the surrounding nebula in a variety of ways, resulting in a complex system of shocks, particles, and energy fields. As the pulsar's radiation collides with the gas and dust in the nebula, it causes the material to glow brightly across multiple wavelengths, including X-rays and radio waves. These interactions are what make the Crab Nebula such an excellent subject for study, as they allow astronomers to observe how radiation, magnetic fields, and particles interact in a controlled but extreme environment. The Crab Nebula is also notable for the unique features of its synchrotron radiation. This type of radiation is emitted by charged particles as they are accelerated in magnetic fields at nearly the speed of light. The Crab Nebula's synchrotron radiation has been studied extensively, providing valuable insights into the processes that drive particle acceleration in cosmic environments. Understanding synchrotron radiation allows us to learn more about how magnetic fields in neutron stars, supernova remnants, and other high-energy environments can accelerate particles to such extreme speeds. These findings are key to understanding how cosmic rays, those high-energy particles that travel through space, are generated. The Crab Nebula also acts as a natural laboratory for studying the behavior of magnetic fields. The neutron star at the center of the nebula is surrounded by a magnetic field that is more than 1 trillion times stronger than the Earth's magnetic field. This immense magnetic field is responsible for many of the nebula's characteristics, from the pulsar's rapid rotation to the emission of radiation and particles. By studying the structure and behavior of the magnetic field in the Crab Nebula, scientists can gain insights into the role that magnetic fields play in astrophysical processes, such as star formation, the behavior of plasma, and the acceleration of high-energy particles. The Crab Nebula is also a remarkable example of how cosmic events shape the larger structure of the universe. When a supernova like the one that created the Crab Nebula occurs, it releases a massive amount of energy and matter into space. This material can then go on to form new stars, planets, and even life. In this way, the death of a star is not truly an end, but rather a continuation of the cosmic cycle that is constantly creating and destroying, shaping the universe in ways that we are only beginning to understand. The elements forged in the core of massive stars are spread throughout the galaxy by supernovae, enriching the interstellar medium and making possible the formation of future generations of stars and planets. This process of stellar evolution, driven by the birth and death of stars, is the engine that powers the cosmos. In many ways, the Crab Nebula represents the interconnectedness of the universe. It's a site where death gives rise to new life, where particles born in the hearts of stars are scattered across space, and where we can see firsthand how the universe is constantly evolving. The study of supernova remnants like the Crab Nebula not only deepens our understanding of the universe's past but also offers clues about its future. The Crab Nebula is a living testament to the ongoing cycles of birth, death, and rebirth that shape the cosmos. One of the most intriguing aspects of the Crab Nebula is its connection to the study of the cosmic microwave background, CMB. The CMB is the faint radiation left over from the Big Bang, the event that created the universe. By studying the Crab Nebula and its energetic processes, scientists can learn more about the conditions of the universe shortly after the Big Bang. For example, the presence of certain elements in the Crab Nebula, as well as the way energy is distributed throughout the nebula, can provide clues about the conditions in the early universe. Understanding the Crab Nebula's energetic processes could ultimately help scientists unlock the mysteries of the CMB and improve our understanding of the universe's origins. Furthermore, the Crab Nebula's unique properties have practical applications for advancing our technological capabilities here on Earth. The study of high-energy radiation and particle acceleration processes in the Crab Nebula has direct implications for developing new technologies in fields such as medical imaging, communications, and energy production. For example, the techniques used to observe and analyze synchrotron radiation from the Crab Nebula are similar to those used in synchrotron light sources on Earth, which are used to study the properties of materials at the atomic level. As scientists continue to study the Crab Nebula, they may discover new ways to harness these processes to benefit humanity. The Crab Nebula also serves as a symbol of human curiosity and the pursuit of knowledge. For centuries, humanity has looked to the stars, asking questions about the nature of the cosmos and our place within it. The study of the Crab Nebula is a continuation of this quest for understanding, a reminder that the mysteries of the universe are not beyond our reach. As we continue to push the boundaries of what we know, the Crab Nebula will remain a key focal point in our exploration of the cosmos. Ultimately, the Crab Nebula reminds us of the power of curiosity and the importance of exploration. It challenges us to continue searching for answers, to ask questions, and to keep pushing the limits of our knowledge. As we study the nebula and its pulsar, we gain not only insight into the workings of the universe but also a deeper appreciation for the cosmic processes that shape our existence. The legacy of the Crab Nebula is one of discovery, inspiration, and the promise of even greater revelations yet to come. As we continue to explore the Crab Nebula, there is so much more to uncover about its influence on our understanding of the cosmos. Beyond the immediate scientific knowledge we gain, there is an even deeper connection that emerges, one that stretches across space and time, affecting everything from the formation of galaxies to the very structure of space itself. The Crab Nebula also provides us with an opportunity to study the extreme environments that exist within supernova remnants. These environments are incredibly harsh, filled with intense radiation, high-energy particles, and powerful magnetic fields. Yet, in the midst of this chaos, we see the formation of order. The nebula itself is a delicate balance of energy and matter, a perfect example of how the universe can take the raw materials from the death of a star and use them to create something extraordinary. The pulsar at the heart of the Crab Nebula is key to this balance. This highly magnetic, rapidly rotating neutron star is a unique object in its own right. It has a density so extreme that it is almost incomprehensible. A neutron star is the remnant of a massive star that has collapsed under its own gravity. When the core of the star collapses, the protons and electrons are crushed together to form neutrons, resulting in an object with the mass of the Sun compressed into a sphere only about 10 to 20 kilometers in diameter. This means that a neutron star is incredibly dense, with the matter inside it packed so tightly that a single cubic centimeter would weigh as much as the entire human population. The Crab pulsar is also an exceptional source of high-energy radiation. The pulsar's rapid rotation causes it to emit beams of electromagnetic radiation from its magnetic poles. As it spins, these beams sweep across space, like a cosmic lighthouse. This periodic emission of radiation is what gives the pulsar its name. It pulses, with regular intervals, as it rotates. The intense radiation emitted by the Crab pulsar can be observed across the entire electromagnetic spectrum, from radio waves to X-rays. The study of this radiation helps scientists understand how magnetic fields, particle acceleration, and high-energy phenomena interact in extreme environments. The pulsar's energy output has profound implications for understanding the behavior of particles at relativistic speeds. The particles in the Crab Nebula, which are accelerated by the pulsar's intense magnetic field, travel at nearly the speed of light. These high-energy particles are responsible for much of the nebula's glow, as they interact with the surrounding gas and dust. The study of these particles helps us better understand the mechanics of cosmic ray production and acceleration, which is a critical area of research in astrophysics. In fact, the Crab Nebula serves as a natural laboratory for studying the physics of high-energy astrophysics. By observing the behavior of particles in such extreme environments, scientists are able to test theories related to plasma physics, quantum mechanics, and the behavior of matter under conditions that are impossible to replicate on Earth. This research not only deepens our understanding of the universe but also enhances our technological capabilities, as the principles discovered in these studies can be applied to fields such as nuclear fusion, particle accelerators, and even space exploration. The Crab Nebula's role as a cosmic laboratory extends beyond just high-energy particles. The magnetic fields present within the nebula are another area of intense study. These fields are responsible for guiding the charged particles that travel through space, creating a complex web of interactions that govern the movement of matter. The strength and structure of these magnetic fields are key to understanding how they influence the dynamics of the nebula and the pulsar. Additionally, studying the interactions between the magnetic fields and the surrounding gas allows scientists to probe the properties of space itself, revealing insights into the nature of the cosmos on the largest scales. The Crab Nebula also provides valuable insight into the processes that govern the evolution of stars. As we mentioned earlier, the Crab Nebula is the remnant of a supernova explosion, the death of a massive star. The star that exploded in the Crab Nebula was a member of a class of stars known as Wolf-Rayet stars. These stars are massive, hot, and short-lived, and they are known for their powerful stellar winds, which blow off vast amounts of material into space. When a Wolf-Rayet star reaches the end of its life, it undergoes a supernova explosion, releasing a tremendous amount of energy, and creating a supernova remnant like the Crab Nebula. Supernova remnants like the Crab Nebula play a crucial role in the life cycle of stars. The explosion disperses elements like oxygen, carbon, and nitrogen into the surrounding space, enriching the interstellar medium and providing the building blocks for the next generation of stars, planets, and even life itself. This process of stellar recycling is a fundamental aspect of the universe's evolution, and the Crab Nebula offers us a glimpse into this process in action. It is a reminder that the death of a star is not an end but a continuation of the cosmic cycle that shapes the universe. As we study the Crab Nebula and other supernova remnants, we gain a deeper understanding of the forces that drive the evolution of galaxies. The elements that are expelled during a supernova are the same elements that make up the planets, stars, and even life as we know it. Without supernovae, the universe would lack the diversity of elements that are necessary for the formation of complex structures. The Crab Nebula is just one example of how the death of a star contributes to the creation of new stars, planets, and life. This idea of cosmic recycling is not just limited to stars. It extends to the very fabric of space itself. The expansion of the universe, the formation of galaxies, and the interactions between dark matter and normal matter are all processes that are influenced by the remnants of supernova explosions. The Crab Nebula, with its pulsar and supernova remnant, serves as a key piece of the puzzle in understanding how the universe works on both small and large scales. It is a testament to the interconnectedness of all things in the cosmos and a reminder that everything, from the smallest particle to the largest galaxy, is part of a greater cosmic cycle. The study of the Crab Nebula also challenges our assumptions about the nature of the universe. For centuries, scientists have been fascinated by the idea that supernovae could create new stars and galaxies. But the discovery of the Crab Nebula has led to new questions about the role that supernova remnants play in the evolution of the universe. The Crab Nebula is one of the most well-studied supernova remnants, yet it continues to reveal new mysteries. Its pulsar, its synchrotron radiation, and its complex magnetic fields all provide clues to understanding the forces that shape the universe on a fundamental level. Each new discovery adds to our understanding of the cosmos and opens the door to new areas of research. As our technology continues to improve, our ability to observe and study objects like the Crab Nebula will only increase. With advancements in telescopes, space observatories, and particle detectors, we will continue to explore the extreme environments of supernova remnants and neutron stars. These studies will not only deepen our understanding of the universe's past but also shape our future. Whether it's through the development of new technologies or the discovery of new phenomena, the study of the Crab Nebula and other cosmic objects will continue to push the boundaries of human knowledge and exploration. The Crab Nebula serves as a symbol of the incredible complexity and beauty of the universe. It's a reminder that even in the death of a star, new life is born. It shows us that the universe is constantly evolving, that every moment is a part of a greater cosmic cycle. As we continue to study the Crab Nebula, we are not just learning about one particular supernova remnant. We are gaining a deeper understanding of the universe itself and our place within it. As we continue to peel back the layers of the Crab Nebula's mysteries, it's important to recognize the profound impact that this supernova remnant has had on the scientific community. The Crab Nebula, with its energetic pulsar and captivating phenomena, offers a glimpse into the future of astrophysics. This particular object, which has long captured the imagination of astronomers, is not only a living testament to a star's explosive end but also a key to understanding some of the most enigmatic processes in the universe. The Crab Nebula continues to serve as a benchmark for understanding a range of high-energy astrophysical phenomena. From its brilliant pulsar to the high-speed particles racing through its nebula, the Crab Nebula provides a unique opportunity to study extreme states of matter, as well as the forces that govern those states. The pulsar, at the center of this cosmic explosion, acts as a laboratory that cannot be recreated on Earth. The energies at play in this part of the universe are so vast, so beyond the scope of what we can generate in terrestrial environments, that studying them allows us to test the limits of current physical theories. As we continue to explore this subject, we must also consider the ways in which the Crab Nebula's history can teach us about the life cycle of stars and the broader cosmic process of birth, death, and rebirth. The supernova explosion that formed the Crab Nebula is not an isolated event in the universe, but part of a much larger process. It plays a role in the enrichment of the interstellar medium, contributing to the creation of new stars, planets, and potentially even life. The Crab Nebula, in all its chaotic beauty, is a part of the cycle of life in the universe, and its story is not one of destruction but of transformation. Understanding how supernovae like the one that created the Crab Nebula shape the universe requires us to look at both the short-term and long-term impacts of these explosions. In the short term, the explosion releases vast amounts of energy, which can impact its immediate surroundings. The shock waves from the explosion of a supernova can compress nearby gas clouds, triggering the formation of new stars. Over a longer period, the expelled elements from the explosion mix with the surrounding interstellar medium, enriching the environment for future generations of stars and planets. This cycle of stellar birth, death, and rebirth is a process that occurs on a galactic scale and contributes to the ongoing evolution of the universe. The Crab Nebula, in particular, offers an example of how the remnants of a single star can leave a lasting imprint on the cosmos. Its pulsar, which serves as a lighthouse in space, continues to emit powerful beams of electromagnetic radiation, while the nebula itself expands outward, filling the surrounding space with the remnants of the explosion. The Crab Nebula is still a dynamic object, with its expansion continuing even today. In this way, it offers a snapshot of the evolution of a supernova remnant, showing us the interplay between matter, energy, and time. Additionally, the Crab Nebula allows us to test some of the most fundamental aspects of physics. The pulsar at its core, for example, is a natural laboratory for studying the properties of neutron stars. The study of neutron stars is crucial to understanding the behavior of matter in extreme conditions. A neutron star, with its intense magnetic fields and ultra-dense core, challenges our understanding of the nature of matter itself. It also provides clues about the behavior of matter in extreme gravitational fields, which can further inform our understanding of black holes and other compact objects in the universe. The Crab Nebula also has a profound impact on our understanding of the relationship between energy and matter. The high-energy particles that are accelerated in the nebula are responsible for the glowing emission of light across the electromagnetic spectrum. This radiation is not only a direct result of the pulsar's activity, but also a testament to the way in which energy is transferred and transformed in space. The Crab Nebula serves as a reminder that the universe is full of processes that are beyond our ability to fully replicate or control on Earth. In a sense, the Crab Nebula represents the universe's ability to bend and shape matter and energy in ways that defy human understanding. Furthermore, the study of the Crab Nebula helps us refine our models of astrophysical processes, particularly those involving high-energy radiation. The radiation emitted by the Crab Nebula has been a subject of intense study, as scientists attempt to understand the mechanisms that drive the acceleration of particles to relativistic speeds. The Crab Nebula's synchrotron radiation, which is generated when charged particles travel at near light speeds through magnetic fields, is one of the key sources of this high-energy radiation. By observing the Crab Nebula's emission spectrum, scientists can learn about the properties of the nebula, the pulsar at its center, and the underlying processes that govern particle acceleration in such an extreme environment. In addition to the scientific advancements that studying the Crab Nebula brings, there is also an underlying philosophical and existential significance to this supernova remnant. The Crab Nebula serves as a reminder of the universe's vast scale and the fleeting nature of time. The explosion that formed the nebula occurred around 1,000 years ago, but the light from that explosion still reaches us today. In this way, the Crab Nebula connects us to the past, offering a glimpse into the life and death of a star that occurred long before humanity existed. Yet, despite the passage of time, the nebula's beauty and power endure, a testament to the timeless forces that shape the universe. The Crab Nebula also challenges our perspective on the nature of existence. In many ways, it forces us to confront the cyclical nature of life and death in the universe. The star that exploded to form the Crab Nebula is gone, but the remnants of its life continue to influence the cosmos in profound ways. This, in turn, raises deeper questions about the nature of life itself. If the death of one star can give rise to the creation of new stars, planets, and even life, then what does this say about the broader cycle of existence in the universe? The story of the Crab Nebula is, at its core, a story of transformation. From the violent explosion of a dying star to the creation of a pulsar and nebula, this supernova remnant exemplifies the constant change and rebirth that define the cosmos. The study of the Crab Nebula offers us not just a deeper understanding of the universe, but also a chance to reflect on our place within it. As we observe the remnants of this ancient explosion, we are reminded that everything in the universe is interconnected, that the life of a star is just a small part of a much larger, ever-evolving process. As technology continues to evolve, the possibilities for studying the Crab Nebula and other cosmic phenomena are virtually limitless. Future missions, both ground-based and space-based, will continue to gather data from this incredible object. New instruments, such as advanced radio telescopes and space observatories, will provide even greater detail about the nebula's structure and the pulsar at its heart. This wealth of data will likely lead to new discoveries about the fundamental workings of the universe and open up even more questions that challenge our understanding of space, time, and matter. The Crab Nebula, therefore, is not just a distant object in the night sky. It is a beacon of discovery, a reminder of the incredible mysteries that lie beyond our world. It invites us to look deeper into the cosmos and contemplate the true nature of existence. The pulsar, the glowing nebula, and the remnants of the supernova all speak to the dynamic, ever-changing nature of the universe and our place within it. As we continue to study and unravel the mysteries of the Crab Nebula, we move ever closer to understanding the forces that govern the universe and the deeper truths that lie hidden among the stars. As we continue our exploration of the Crab Nebula, it's important to highlight the far-reaching significance of this celestial object. It serves not only as a natural laboratory for astrophysicists, but also as a cultural symbol of the incredible scale and complexity of the universe. The Crab Nebula challenges our understanding of time, space, and matter, compelling us to think about the cosmos in ways that are beyond our daily experience. Its pulsar, at the heart of the nebula, emits a rhythmical beat that reverberates across space and time, acting as a cosmic clock that offers insights into the fundamental workings of the universe. The study of the Crab Nebula thus provides a deep connection between the cosmic and the philosophical, linking the physical realities of space with the profound questions of our existence. One of the most captivating aspects of the Crab Nebula is its pulsar, the rapidly rotating neutron star that sits at its center. The pulsar's powerful magnetic field and rapid rotation make it one of the most energetic objects in the universe. This stellar remnant, about the size of a city but with a mass greater than that of the Sun, is a direct result of the supernova explosion that gave birth to the nebula. The pulsar's rotation is so rapid that it completes one full spin every 33 milliseconds. This means that it emits beams of electromagnetic radiation with extraordinary regularity, like a cosmic lighthouse sending out pulses of light. These pulses are detectable across vast distances, making the Crab Nebula one of the most well-studied objects in the sky. The pulsar at the center of the Crab Nebula also generates an immense amount of energy, much of which is released in the form of high-energy particles. These particles are accelerated to nearly the speed of light by the pulsar's magnetic field, creating a region around the pulsar known as the pulsar wind nebula. This pulsar wind is a highly energetic outflow of particles that interacts with the surrounding nebula, creating complex shockwaves and radiation across the electromagnetic spectrum. This interaction between the pulsar's wind and the nebula's gas and dust is what gives the Crab Nebula its distinctive appearance, and allows astronomers to study the high-energy processes occurring in the region. The Crab Nebula is also a unique source of synchrotron radiation, a form of electromagnetic radiation that occurs when charged particles move at speeds close to the speed of light through a magnetic field. The Crab Nebula's synchrotron radiation is responsible for the bright emissions across a wide range of wavelengths, from radio waves to X-rays and gamma rays. By studying the Crab Nebula's radiation across these different wavelengths, scientists can learn more about the particle acceleration processes occurring in the nebula and gain insights into the behavior of matter in extreme conditions. These observations provide invaluable data that helps refine our models of particle physics, astrophysics, and the behavior of magnetic fields in space. The Crab Nebula's high-energy environment also provides a fascinating context for the study of cosmic rays, which are high-energy particles that travel through space at nearly the speed of light. The Crab Nebula is a significant source of these cosmic rays, which are believed to play a key role in the distribution of matter and energy throughout the universe. Cosmic rays can provide valuable information about the conditions in the nebula and the processes that drive particle acceleration in such extreme environments. They also offer a window into the larger-scale structure of the universe, as cosmic rays travel across vast distances and provide clues about the interstellar medium, magnetic fields, and the dynamics of galaxies. Moreover, the Crab Nebula continues to be a crucial object for understanding the life cycle of stars and the processes that lead to their ultimate demise. The supernova that created the nebula is thought to have occurred around the year 1054, and the explosion was witnessed by astronomers on Earth. This historical event provides a unique opportunity to study the aftermath of a supernova explosion and understand the long-term evolution of a supernova remnant. The nebula itself continues to expand, with its outer edges moving outward at speeds of up to 1,500 kilometers per second. This expansion will continue for thousands of years, gradually dispersing the material from the explosion into the interstellar medium, where it will contribute to the formation of new stars and planets. In the context of stellar evolution, the Crab Nebula is an important example of the fate of massive stars. When a star reaches the end of its life and runs out of fuel, its core collapses under the force of gravity, causing the outer layers to explode in a supernova. The core left behind after the explosion becomes a neutron star, a dense and highly magnetized remnant that contains more mass than the Sun but is only a few kilometers in diameter. The Crab Nebula's pulsar is an example of such a neutron star, and its study provides crucial information about the properties of neutron stars, including their magnetic fields, rotation, and the behavior of matter under extreme pressure and temperature. The Crab Nebula is also a key object for studying the dynamics of supernova remnants, which are the expanding clouds of gas and dust left behind after a supernova explosion. These remnants are often the site of intense shock waves, as the explosion causes the surrounding gas to compress and heat up. In the case of the Crab Nebula, the interaction between the supernova shock wave and the surrounding interstellar medium has created a complex structure of filaments and knots of gas, which are visible in the nebula's glowing emissions. The study of these structures helps scientists understand how supernova remnants evolve over time and how they interact with the surrounding environment. In addition to the scientific discoveries that the Crab Nebula has contributed to, it also has cultural significance. The nebula's history is tied to one of the most famous supernova events in recorded history, the explosion observed by Chinese astronomers in 1054. This explosion was so bright that it was visible during the day for weeks, and it was recorded in historical records from across Asia. The supernova was later named SN 1054, and its aftermath created the Crab Nebula, which remains one of the most studied objects in the night sky. The Crab Nebula serves as a reminder of the long history of human curiosity and the quest to understand the universe. The study of the Crab Nebula continues to inspire new generations of scientists, astronomers, and stargazers. It represents both the fragility and resilience of the cosmos, showing us that even in the aftermath of a cataclysmic explosion, new forms of life and energy can emerge. As we continue to study the Crab Nebula, we are reminded that the universe is full of mysteries waiting to be unraveled, and that the more we learn, the more we realize how much we still have to discover. Looking ahead, the future of Crab Nebula research holds immense promise. With the development of new technologies and advanced telescopes, scientists will be able to study the nebula in even greater detail. The study of the pulsar at the center of the nebula will likely reveal new insights into the behavior of matter in extreme conditions, and the Crab Nebula's role in the larger-scale dynamics of the galaxy will continue to be explored. The nebula's synchrotron radiation, its cosmic rays, and its pulsar wind all offer new avenues for scientific discovery, and as our understanding of these phenomena deepens, we will be able to unlock even more of the Crab Nebula's secrets. The Crab Nebula is a shining example of the universe's ability to create and destroy, to transform and evolve. It is a symbol of the incredible power of supernovae and the lasting impact they have on the surrounding cosmos. The pulsar at its center, with its rapid rotation and intense magnetic field, offers a glimpse into the extreme conditions that govern the universe. The nebula itself is a dynamic, ever-evolving object, and its study provides invaluable insights into the nature of stars, black holes, neutron stars, and the very fabric of space and time. The Crab Nebula reminds us that the universe is a place of constant change and discovery, where the forces of nature can create and destroy on scales that are beyond our comprehension. It is a cosmic laboratory that continues to challenge our understanding and inspire our curiosity. As we continue to study the Crab Nebula, we will no doubt uncover new mysteries and gain a deeper appreciation for the beauty and complexity of the universe. The Crab Nebula continues to stand as a testament to the incredible power and complexity of the universe. Its multifaceted nature provides a wealth of opportunities for scientists to delve into some of the most profound questions about the cosmos. As we push the boundaries of our technological and theoretical capabilities, the nebula serves as both a guide and a mystery, challenging us to innovate and rethink what we know about the universe. One of the most fascinating aspects of the Crab Nebula is its dynamic evolution over time. Despite its relatively young age in astronomical terms, less than 1,000 years, it has already undergone significant transformations. The nebula's outer edges are expanding rapidly, while its internal structures are constantly shaped by the pulsar wind and magnetic fields. This continuous change is a vivid demonstration of how energy and matter interact in the aftermath of a supernova explosion. By studying the nebula's evolution, scientists can develop better models of how such remnants develop over millennia and what role they play in the galactic ecosystem. The pulsar at the heart of the Crab Nebula is not just a source of fascination for its rotational speed and magnetic field but also for its implications in the study of relativity and quantum mechanics. The extreme conditions present in the pulsar challenge our current understanding of physics, offering a natural laboratory to test theories under conditions that cannot be replicated on Earth. For instance, The intense gravitational field of the pulsar provides an excellent opportunity to study general relativity, while the behavior of matter under such extreme densities pushes the boundaries of quantum mechanics. Another intriguing aspect of the Crab Nebula is its role in high-energy astrophysics. The nebula is a prolific emitter of gamma rays, which are the most energetic form of electromagnetic radiation. These gamma rays originate from the acceleration of particles within the nebula, driven by the pulsar's magnetic field. Observing and analyzing these emissions allows scientists to study the mechanisms of particle acceleration and energy transfer in extreme environments. This research has implications beyond astrophysics, as it also contributes to our understanding of plasma physics and the behavior of charged particles in high-energy conditions. The Crab Nebula's synchrotron radiation is another area of ongoing study. This radiation, produced by high-energy electrons spiraling through magnetic fields, is not only a defining feature of the nebula but also a key to understanding its internal processes. The radiation spans a broad range of wavelengths, from radio waves to gamma rays, making the Crab Nebula one of the most versatile objects in the electromagnetic spectrum. By analyzing the synchrotron radiation, scientists can trace the movement of particles, map magnetic fields, and identify regions of intense activity within the nebula. Additionally, the Crab Nebula serves as a reference point for calibrating astronomical instruments. Its consistent brightness and well-understood properties make it an ideal target for testing and fine-tuning the sensitivity of telescopes and detectors. This role is crucial for the broader field of astronomy, as it ensures that observations of other celestial objects are accurate and reliable. The Crab Nebula's importance as a calibration tool underscores its value not just as a subject of study but also as a cornerstone of observational astronomy. The nebula's historical significance also cannot be overstated. The supernova that created the Crab Nebula was one of the brightest and most widely observed celestial events in recorded history. Its appearance in 1054 was documented by astronomers. These historical accounts have been instrumental in understanding the timing and nature of the supernova, offering a unique perspective on the nebula's origins. The fusion of historical records and modern science creates a rich narrative that connects humanity's past with its ongoing exploration of the cosmos. Looking forward, the study of the Crab Nebula will likely benefit from advances in technology and methodology. Future telescopes, such as the James Webb Space Telescope and next-generation gamma-ray observatories, will provide unprecedented views of the nebula, revealing details that were previously inaccessible. These observations will help answer lingering questions about the nebula's structure, composition, and energy dynamics, while also uncovering new mysteries that will drive the next wave of research. The Crab Nebula also has the potential to shed light on the origins and evolution of cosmic rays. These high-energy particles, which travel through space at nearly the speed of light, are thought to originate in part from supernova remnants like the Crab Nebula. By studying the nebula's emission of cosmic rays, scientists can gain insights into how these particles are accelerated and how they interact with the interstellar medium. This research has far-reaching implications, as cosmic rays play a crucial role in shaping the physical and chemical properties of galaxies. In the broader context of the universe, the Crab Nebula serves as a reminder of the interconnectedness of all things. The elements released during the supernova explosion, such as carbon, oxygen, and nitrogen, will eventually be incorporated into new stars, planets, and possibly even life forms. This cycle of creation and destruction is a fundamental aspect of the cosmos, and the Crab Nebula provides a vivid illustration of this process. It is a cosmic crucible where the building blocks of life are forged, scattered, and redistributed, contributing to the ongoing evolution of the universe. The pulsar's clock-like precision also offers intriguing possibilities for future research. Its consistent emissions could serve as a natural timekeeping system for studying changes in the Earth's rotation, the dynamics of the solar system, and even gravitational waves. The pulsar's signals are so regular that they have been used as a reference for testing the stability of atomic clocks and other timekeeping devices. This dual role as both a scientific object and a practical tool highlights the multifaceted nature of the Crab Nebula and its central pulsar. As we continue to explore the mysteries of the Crab Nebula, It is clear that this remarkable object has much to teach us about the universe and our place within it. Its beauty, complexity, and scientific significance make it a source of endless fascination and inspiration. The Crab Nebula challenges us to think beyond the limits of our current understanding, to ask new questions, and to seek answers in the vast expanse of space. The legacy of the Crab Nebula is one of discovery and wonder. It connects us to the past, illuminates the present, and points the way to the future. As we gaze at the nebula through telescopes and ponder its mysteries, we are reminded of the boundless potential of human curiosity and the infinite possibilities of the universe. The Crab Nebula is more than just a remnant of a supernova. It is a beacon of knowledge, a testament to the power of science, and a symbol of our enduring quest to understand the cosmos. The Crab Nebula, with its swirling tendrils of gas and vibrant energy emissions, remains one of the most compelling celestial phenomena humanity has ever encountered. Beyond its scientific importance, the nebula holds a mirror to some of the most profound philosophical and existential questions about the universe and our place within it. Why do stars die in such cataclysmic ways? How does their death contribute to the genesis of new stars and planets? What can the intricate processes within the Crab Nebula teach us about the life cycle of matter and energy in the cosmos? One particularly fascinating feature of the Crab Nebula is its dynamic interplay of forces. At the heart of the nebula lies the pulsar, a neutron star spinning with extraordinary precision. This spinning remnant is the engine driving much of the nebula's activity. With its intense magnetic fields and rapid rotation, the pulsar accelerates particles to near-light speeds, generating a wind of high-energy electrons and positrons that sculpt the nebula's intricate structure. This interplay between the pulsar wind and the surrounding nebula creates a vibrant dance of energy, continuously reshaping the glowing tendrils of gas and dust that we observe. The synchrotron radiation emitted by the accelerated particles is not only visually striking but also an invaluable source of data for astronomers. This radiation allows scientists to probe the conditions within the nebula, offering insights into the behavior of particles under extreme conditions. The Crab Nebula serves as a natural particle accelerator, enabling us to study phenomena that would otherwise be impossible to replicate in laboratory settings on Earth. This knowledge has applications beyond astrophysics, influencing fields such as plasma physics and materials science. The nebula's high-energy gamma-ray emissions also hold immense significance. Observations of these emissions reveal the presence of particles moving at relativistic speeds, hinting at the underlying mechanisms of energy transfer within the nebula. Gamma rays are the most energetic form of electromagnetic radiation, and their detection requires highly sensitive instruments. Space-based observatories, such as the Fermi Gamma-Ray Space Telescope, have provided invaluable data on the Crab Nebula's gamma-ray activity, revealing flares and bursts that challenge existing theoretical models. One of the most intriguing aspects of these gamma-ray flares is their unpredictability. Unlike the steady emissions of the pulsar, these flares appear suddenly and can be incredibly intense. Their origins remain a mystery, with some theories suggesting they may arise from magnetic reconnection events within the pulsar wind. Understanding these flares could unlock new insights into magnetic field interactions and particle acceleration processes, with implications for our understanding of similar phenomena in other astrophysical contexts. The Crab Nebula also plays a pivotal role in the study of cosmic rays. These high-energy particles, which travel through space at nearly the speed of light, originate from a variety of sources, including supernova remnants. The nebula's environment provides an ideal setting for studying how these particles are accelerated and how they interact with magnetic fields and interstellar matter. By analyzing the cosmic rays emanating from the Crab Nebula, scientists can refine their models of particle acceleration and explore the broader role of supernova remnants in shaping the galaxy. Historically, the Crab Nebula has also been a bridge between ancient observations and modern science. The supernova that created the nebula was one of the brightest celestial events ever recorded, leaving an indelible mark on the night skies of 1054 AD. Ancient astronomers from various cultures documented the event, providing a rare intersection of historical records and modern astrophysical data. These accounts have been instrumental in pinpointing the timing of the explosion and understanding the nebula's early evolution. They remind us that our quest to understand the universe is a continuum, spanning generations and cultures. The Crab Nebula's rich tapestry of mysteries also inspires questions about the broader life cycle of stars and their remnants. What determines the fate of a star after it exhausts its nuclear fuel? Why do some stars end their lives in relatively quiet transitions, while others explode with such ferocity? The Crab Nebula provides a unique lens through which to examine these questions, offering clues about the factors that influence the outcome of stellar evolution. The nebula's chemical composition is another area of intense study. The supernova explosion that created the Crab Nebula scattered elements like carbon, oxygen, and nitrogen into space, elements that are essential for the formation of planets and life. By analyzing the spectral signatures of these elements, scientists can trace their distribution within the nebula and beyond. This research underscores the interconnectedness of cosmic phenomena, showing how the death of one star can seed the birth of new worlds. In a broader sense, the Crab Nebula challenges us to think about the universe's cycles of creation and destruction. It is a reminder that the cosmos is in a constant state of flux, with stars forming, living, and dying in an intricate dance that spans billions of years. The nebula's story is a microcosm of this larger narrative, offering a snapshot of one moment in the cosmic timeline. It invites us to ponder our own place in this grand tapestry, encouraging both humility and wonder. As our technological capabilities continue to advance, the Crab Nebula will undoubtedly remain a focal point of astronomical research. Future missions and observatories will provide even more detailed views of the nebula, revealing new layers of complexity and uncovering phenomena that we can scarcely imagine today. The nebula's role as a cosmic laboratory will continue to inspire generations of scientists, fueling discoveries that extend far beyond its boundaries. The Crab Nebula is more than just a remnant of a supernova. It is a symbol of the universe's boundless creativity and power. Its intricate structures, dynamic processes, and rich history make it a source of endless fascination. By studying the Crab Nebula, we gain not only a deeper understanding of the cosmos but also a renewed appreciation for the mysteries that lie at the heart of existence. It is a reminder that the universe is far more complex and beautiful than we can ever fully comprehend, and that our quest to understand it is a journey without end. The Crab Nebula's importance as a scientific treasure trove cannot be overstated. Its pulsar, energetic emissions, and vivid gas clouds provide a glimpse into the aftermath of a supernova, shedding light on some of the most extreme environments in the universe. However, the Crab Nebula also holds broader implications for our understanding of cosmic interconnectedness, serving as a reminder that the death of a star is not merely an end but a beginning, a seed for new cosmic evolution. Let's delve deeper into the pulsar at the heart of the nebula. Pulsars are a specific type of neutron star, born from the collapsed core of a massive star that has gone supernova. What makes them unique is their incredible density, rotation speed, and intense magnetic fields. The Crab pulsar, in particular, rotates approximately 30 times per second, sending out beams of electromagnetic radiation like a cosmic lighthouse. These beams sweep across the cosmos, and when they intersect with Earth, we detect them as regular pulses of radio waves, visible light, X-rays, and gamma rays. What's astonishing about the Crab pulsar is how well it adheres to predictable behavior, yet it also defies expectations in significant ways. Its consistency allows astronomers to use it as a kind of cosmic clock. However, the occasional glitches, sudden, small increases in its rotational speed, continue to puzzle researchers. These glitches are believed to result from internal changes in the pulsar, such as shifts in its superfluid interior or its solid crust. These events provide invaluable insights into the physics of neutron stars, which remain some of the most enigmatic objects in the universe. The Crab Nebula's unique pulsar wind nebula, a result of its pulsar's energetic outflows, is another area of intense study. This wind is composed of highly relativistic particles, electrons and positrons, that interact with the surrounding magnetic fields. As these particles spiral along magnetic field lines, they emit synchrotron radiation, which creates the nebula's characteristic glow. By studying the morphology and spectral properties of this radiation, astronomers can infer details about the magnetic fields and particle acceleration mechanisms within the nebula. The surrounding nebula also exhibits striking asymmetry, with regions of varying brightness and density. This irregularity hints at the chaotic nature of the supernova explosion that created it, as well as the interactions between the pulsar wind and the surrounding material. The Crab Nebula's filaments, composed of ionized gas and dust, showcase the remnants of the progenitor star's outer layers, flung outward during the explosion. These filaments glow due to heating from the nebula's energetic radiation and provide clues about the star's original composition and structure. Another fascinating feature of the Crab Nebula is its high-energy gamma-ray flares, which are among the most energetic events ever observed in astrophysics. These flares are puzzling because they involve particles being accelerated to energies far beyond what scientists had previously thought possible. Theories suggest that these flares may originate from magnetic reconnection events, sudden, violent rearrangements of magnetic field lines, that release enormous amounts of energy. Studying these flares not only enhances our understanding of the Crab Nebula but also has implications for other astrophysical systems, such as active galactic nuclei and gamma-ray bursts. The Crab Nebula also plays a significant role in calibrating astronomical instruments. Because its emissions are relatively steady over time, the nebula serves as a reference source for calibrating telescopes and detectors across the electromagnetic spectrum. This utility extends its influence far beyond its own boundaries, making it an essential tool for studying other objects in the cosmos. From a historical perspective, the Crab Nebula connects us to ancient skywatchers. The supernova that created it was bright enough to be visible during the daytime for several weeks and was meticulously documented by Chinese and Japanese astronomers in 1054 AD. These historical records, combined with modern observations, allow us to trace the nebula's evolution over nearly a millennium. Such a long baseline of data is invaluable for understanding the dynamics of supernova remnants and the life cycle of pulsars. In many ways, the Crab Nebula embodies the interplay of destruction and creation that defines the universe. Its progenitor star, once a beacon of nuclear fusion and light, met a violent end, scattering its elements into the cosmos. These elements, carbon, oxygen, nitrogen, and others, are the building blocks of planets, life, and everything we see around us. The nebula is a testament to the fact that stars not only illuminate the universe during their lifetimes, but also shape its future through their deaths. On a broader scale, the Crab Nebula challenges our understanding of the universe's extremes. It is a natural laboratory for studying phenomena that push the boundaries of physics, from relativistic particle acceleration to magnetic field interactions. It forces us to refine our models of how matter and energy behave under extreme conditions and inspires new questions about the nature of the cosmos. Despite decades of study, the Crab Nebula still holds mysteries waiting to be unraveled. Future advancements in telescope technology and observational techniques will undoubtedly reveal new layers of complexity, further enriching our understanding of this remarkable object. Missions like the James Webb Space Telescope, with its unprecedented sensitivity and resolution, promise to unlock even more secrets, shedding light on the nebula's intricate processes and interactions. The Crab Nebula serves as a reminder of the vastness and complexity of the universe. It invites us to look beyond our immediate surroundings and consider the forces that shape the cosmos on grand scales. It is a symbol of both the fragility and resilience of matter, a story of death giving rise to new beginnings, and a testament to the unending cycle of creation and destruction that defines existence. The Crab Nebula is more than just a celestial phenomenon. It is a beacon of wonder, a source of inspiration, and a gateway to the mysteries of the universe. It reminds us of the infinite possibilities that lie beyond our world and the boundless potential of human curiosity to explore and understand them. The story of the Crab Nebula, from its explosive birth to its continued evolution, is a testament to the dynamic and ever-changing nature of the universe. Its study has transformed not only our understanding of supernova remnants, but also the very principles of astrophysics that guide our exploration of the cosmos. The nebula's influence reaches far and wide, connecting the realms of particle physics, magnetohydrodynamics, and cosmic evolution in ways that were once unimaginable. The Crab Nebula's pulsar, with its rapid rotation and intense energy output, is a marvel in its own right. Despite its relatively small size, roughly 20 kilometers in diameter, it contains more mass than the Sun, compressed into an incredibly dense state. To put this into perspective, a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. This density gives neutron stars their extraordinary gravitational fields and enables phenomena like gravitational lensing, where the star's gravity bends light from nearby objects. The pulsar's magnetic field, another key feature, is trillions of times stronger than Earth's magnetic field. This extreme magnetism is responsible for many of the pulsar's emissions and interactions. As the pulsar rotates, its magnetic poles sweep through space, accelerating charged particles and generating beams of radiation. These beams, as they cross our line of sight, produce the characteristic pulsing signals detected by radio telescopes and other instruments. What's even more fascinating is the energy balance within the nebula. The pulsar serves as the engine that powers the nebula, continuously pumping energy into its surroundings. This energy drives the creation of shock waves, particle acceleration, and the emission of radiation across the electromagnetic spectrum. The delicate interplay between the pulsar's outflows and the nebula's structure creates a dynamic system that evolves over time, revealing new features and behaviors with each observation. The Crab Nebula also serves as a natural particle accelerator, capable of propelling particles to energies far beyond what human-made accelerators like the Large Hadron Collider can achieve. These particles, traveling at nearly the speed of light, provide a unique opportunity to study the physics of high-energy phenomena. By analyzing the interactions between these particles and the nebula's magnetic fields, scientists can gain insights into processes that occur in other extreme environments, such as the vicinity of black holes or the jets of active galaxies. One particularly intriguing aspect of the Crab Nebula is its role in gamma-ray astronomy. The nebula emits gamma rays with energies reaching into the tera-electronvolt (TeV) range, making it one of the brightest gamma-ray sources in the sky. These emissions are believed to result from the synchrotron and inverse Compton scattering processes, where high-energy particles interact with magnetic fields and photons to produce gamma rays. Observations of these emissions help refine our models of particle acceleration and radiation mechanisms, offering a window into the most energetic processes in the universe. The nebula's visual appearance, with its intricate filaments and glowing regions, is another area of fascination. These structures are not static but constantly changing, driven by the complex dynamics of the nebula's environment. High-resolution images from telescopes like the Hubble Space Telescope have revealed stunning details, including wispy tendrils of gas and dust, bright knots of emission, and regions of intense turbulence. These features are a testament to the chaotic yet ordered nature of the nebula, where forces of creation and destruction coexist in a delicate balance. As we look to the future, the Crab Nebula remains a focus of ongoing research. New telescopes and observational platforms, such as the Square Kilometer Array (SK) and the Cherenkov Telescope Array (CTA), promise to uncover even more about this enigmatic object. These instruments will provide unprecedented sensitivity and resolution, enabling scientists to probe the nebula's smallest scales and most subtle features. They may also reveal connections between the Crab Nebula and other astrophysical phenomena, deepening our understanding of the universe as a whole. The enduring allure of the Crab Nebula lies in its ability to surprise and challenge us. It defies simple explanations, pushing the boundaries of our knowledge and inspiring new questions. Each discovery about the nebula adds another piece to the puzzle of cosmic evolution, bringing us closer to understanding the fundamental forces that shape our universe. In contemplating the Crab Nebula, we are reminded of the vastness and complexity of the cosmos. It is a symbol of the incredible processes that govern the life and death of stars, the intricate interplay of matter and energy, and the unending cycle of creation and destruction that defines the universe. Above all, it is a testament to the power of human curiosity and the enduring quest to unravel the mysteries of the cosmos. This connection between historical records and modern astrophysics is a rare and precious phenomenon. Few other celestial objects have such well-documented origins. By comparing ancient descriptions of the supernova's brightness and duration with modern data on the Crab Nebula's expansion and energy output, scientists can create detailed models of the original explosion. These models not only enhance our understanding of the Crab Nebula but also provide insights into other supernova remnants that lack such historical context. The Crab Nebula also offers a unique perspective on the interconnectedness of the cosmos. The elements forged in its progenitor star and expelled during the supernova, carbon, oxygen, nitrogen, and heavier elements, are the building blocks of planets and life. This stellar alchemy is a cornerstone of cosmic evolution, demonstrating how the life cycles of stars contribute to the formation of new generations of stars, planets, and even living organisms. In this sense, the Crab Nebula is not just a relic of destruction but also a symbol of renewal and creation. The role of the Crab Nebula in modern astronomy extends to its utility as a calibration tool for instruments. Its consistent emissions across multiple wavelengths make it an ideal standard for calibrating telescopes and detectors. This reliability ensures that observations of other celestial objects are accurate and comparable, furthering our exploration of the universe. The nebula's significance as a reference source underscores its broader impact on the field of astrophysics, influencing studies far beyond its immediate environment. One of the most exciting aspects of the Crab Nebula is its potential to unlock new physics. The high-energy gamma-ray flares observed within the nebula challenge existing theories about particle acceleration and magnetic field dynamics. These flares occur on remarkably short timescales, suggesting that they are driven by processes that operate at the limits of our current understanding. Some scientists propose that these events could involve exotic phenomena, such as quantum magnetic reconnection or turbulence at relativistic speeds. Additionally, the Crab Nebula has become a focal point for multi-messenger astronomy, a burgeoning field that combines observations of electromagnetic radiation, gravitational waves, and neutrinos to study cosmic events. While no gravitational waves or neutrinos have yet been detected from the Crab Nebula, its energetic activity makes it a prime candidate for future discoveries. Such detections would provide a new dimension of understanding, revealing the interplay between matter, energy, and space-time in one of the universe's most dynamic environments. Another intriguing avenue of research involves the interaction between the Crab Nebula and the interstellar medium, ISM. As the nebula expands, it collides with the surrounding ISM, creating shock waves and altering the local environment. These interactions can reveal information about both the nebula's structure and the properties of the ISM. For example, variations in the nebula's expansion rate can indicate differences in the density and composition of the surrounding gas and dust. This interplay provides a more comprehensive picture of how supernova remnants influence their cosmic neighborhoods. The Crab Nebula also serves as a reminder of the limits of human perception. Despite its brilliance and complexity, much of its activity occurs in wavelengths that are invisible to the naked eye, such as X-rays and gamma rays. Instruments like the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope allow us to peer into these hidden realms, revealing details that would otherwise remain unknown. This capability underscores the importance of technological innovation in expanding our understanding of the universe. In cultural terms, the Crab Nebula has inspired awe and curiosity for centuries. Its dramatic origins and vibrant appearance have made it a source of wonder for astronomers, artists, and storytellers alike. It symbolizes the grandeur and mystery of the cosmos, reminding us of our place in a universe that is both ancient and ever-changing. Its story, from the explosion that created it to its ongoing evolution, is a testament to the beauty and power of the natural world. As we continue to study the Crab Nebula, it remains a beacon of discovery, challenging us to ask new questions and seek deeper understanding. It is a reminder that even in the aftermath of cosmic destruction, there is immense beauty and endless potential for learning. The nebula's legacy is not just its physical presence in the sky but also the inspiration it provides to generations of scientists and dreamers who look to the stars in search of answers. The Crab Nebula is more than a scientific object, it is a symbol of the interconnectedness of all things. From the elements forged in its heart to the insights gained from its study, it demonstrates how the universe is a tapestry woven from countless threads, each contributing to the whole. It is a story of transformation, resilience, and the unending quest to understand the cosmos. The Crab Nebula's ability to captivate and inform lies not just in its extraordinary beauty but also in the scientific revelations it continues to provide. One of its most fascinating contributions is to our understanding of pulsars, which were first discovered in the 1960s. The pulsar within the Crab Nebula, officially known as PSRB 0531+21, was among the earliest discovered and remains one of the most studied. This spinning neutron star rotates about 30 times per second, emitting a pulse of radiation with each rotation, creating a cosmic lighthouse, effect that can be detected across vast distances. The precise timing of these pulses has allowed scientists to delve into the intricate mechanics of neutron stars. Unlike many pulsars, the Crab pulsar exhibits irregularities in its spin rate, known as glitches. These sudden changes in rotational speed are thought to result from interactions between the star's crust and its superfluid core. By studying these glitches, researchers gain valuable insights into the exotic states of matter that exist under the extreme pressures and densities within neutron stars, conditions that cannot be replicated on Earth. Another aspect of the Crab pulsar that continues to puzzle astronomers is its emission of gamma-ray flares. These flares, which can reach intensities thousands of times greater than the pulsar's typical output, occur sporadically and without warning. The exact mechanism behind these flares remains a mystery, but they are believed to involve rapid changes in the star's magnetic field. Understanding these events could shed light on the behavior of magnetic fields in other astrophysical settings, such as black holes and magnetars. The nebula surrounding the pulsar is no less intriguing. It is powered by the pulsar wind, a stream of high-energy particles accelerated by the pulsar's intense magnetic field. These particles interact with the nebula's magnetic field, producing synchrotron radiation that spans the electromagnetic spectrum, from radio waves to X-rays. This radiation creates the Crab Nebula's iconic glow, and provides a wealth of information about the physical conditions within the nebula. One of the most striking features of the Crab Nebula is its series of moving wisps, which are caused by the interaction between the pulsar wind and the surrounding material. These wisps, visible in high-resolution images, appear to ripple outward from the pulsar like waves on a pond. Their motion is not random but follows patterns dictated by the pulsar's rotation and the structure of the magnetic field. By studying these patterns, astronomers can infer details about the pulsar wind's composition and the dynamics of the nebula. The Crab Nebula is also a source of cosmic rays, which are high-energy particles that travel through space at nearly the speed of light. While most cosmic rays originate from outside the solar system, some are believed to be produced within the nebula itself. These particles provide a unique opportunity to study the processes that accelerate cosmic rays to such extreme energies, offering insights into phenomena that occur in other parts of the universe. In addition to its contributions to high-energy astrophysics, the Crab Nebula plays a key role in our understanding of supernova remnants. The nebula is one of the youngest and most well-preserved remnants known, making it an ideal laboratory for studying the aftermath of a supernova explosion. By comparing the Crab Nebula to older remnants, scientists can trace the evolution of these structures over time and learn how they interact with the surrounding interstellar medium. The nebula's unique characteristics have made it a favorite target for telescopes and observatories around the world. Instruments like the Hubble Space Telescope, the Very Large Array, and the Chandra X-ray Observatory have provided unprecedented views of the nebula's intricate structures, revealing details that were once unimaginable. These observations have not only deepened our understanding of the Crab Nebula but also advanced the field of observational astronomy as a whole. On the theoretical front, the Crab Nebula has inspired numerous models and simulations aimed at explaining its complex behavior. These models incorporate a wide range of physical processes, from magnetohydrodynamics to particle acceleration, and have become increasingly sophisticated over time. While no single model can capture all the nuances of the nebula, the interplay between theory and observation has led to significant advances in our understanding of astrophysical phenomena. Culturally, the Crab Nebula has left an indelible mark on human imagination. Its origins in a supernova observed nearly a millennium ago connected to ancient stargazers, while its modern study represents the cutting edge of scientific inquiry. It serves as a reminder of how far we have come in our quest to understand the cosmos, and how much remains to be discovered. As we continue to explore the Crab Nebula, it remains a symbol of the universe's power, beauty, and mystery. It challenges us to push the boundaries of knowledge and to embrace the wonder of discovery. Whether viewed through the lens of science, history, or art, the Crab Nebula is a testament to the interconnectedness of all things and the enduring human spirit of curiosity. The Crab Nebula continues to act as a bridge between ancient observations and the cutting-edge scientific tools of our era, embodying the timeless pursuit of understanding our place in the cosmos. While its luminous beauty and intricate details captivate the imagination, its scientific significance runs far deeper, offering critical insights into phenomena that define the universe. From a physical perspective, the Crab Nebula represents an active snapshot of a supernova remnant that is still evolving. As the shockwaves from the initial explosion continue to expand outward, they collide with interstellar material, causing ripples of interaction that reveal details about the nebula's internal structure and its surrounding environment. This ongoing interaction provides insights into the life cycles of stars, the properties of the interstellar medium, and the mechanics of shockwave propagation. The pulsar at the heart of the Crab Nebula adds another layer of intrigue. Its 30-millisecond rotation period is both a testament to the extreme conditions under which neutron stars form and a tool for probing the laws of physics in these extreme environments. The intense gravitational forces, rapid rotation, and strong magnetic fields present in the Crab pulsar offer a natural laboratory for testing theories about matter and energy under conditions that are impossible to recreate on Earth. One particularly compelling area of research involves the pulsar's magnetic field, which is among the most powerful in the universe. The interaction between this field and the pulsar wind creates a complex, dynamic system that drives the nebula's emissions. By studying these emissions, scientists can learn about the behavior of charged particles in strong magnetic fields, a topic with implications for understanding phenomena ranging from solar flares to the jets of active galactic nuclei. Another feature that makes the Crab Nebula unique is its broad emission spectrum, which spans radio waves to gamma rays. Each part of the spectrum provides different information about the nebula's physical properties. For instance, radio waves reveal details about the distribution of electrons within the nebula, while X-rays and gamma rays provide clues about the highest energy processes occurring near the pulsar. The synchrotron radiation that dominates much of the nebula's emission is a key focus of study, as it offers insights into particle acceleration mechanisms that operate across the universe. The high-energy gamma-ray flares observed in the Crab Nebula have posed significant challenges to existing models of pulsar wind nebulae. These flares occur unexpectedly and on short timescales, releasing immense amounts of energy. Their origins remain a topic of active research, with hypotheses ranging from magnetic reconnection events to turbulence within the pulsar wind. These phenomena push the boundaries of our understanding of high-energy astrophysics and highlight the need for continued observation and theoretical development. The Crab Nebula also plays a pivotal role in the emerging field of multi-messenger astronomy. While it has not yet been a source of detected gravitational waves or neutrinos, its energetic activity and historical significance make it a prime candidate for future observations. Multi-messenger astronomy aims to combine data from different types of signals, electromagnetic radiation, gravitational waves, and neutrinos, to provide a more comprehensive picture of cosmic events. The Crab Nebula's contributions to this field could be transformative, offering new ways to explore the universe. On a larger scale, the Crab Nebula serves as a microcosm of cosmic processes that occur throughout the universe. The elements created in the supernova explosion, carbon, oxygen, and heavier elements, are the building blocks of planets and life. As the nebula expands and its material mixes with the interstellar medium, these elements become part of the next generation of stars and planetary systems. This cycle of creation and destruction is fundamental to the evolution of galaxies and the universe as a whole. The Crab Nebula's role as a calibration tool for astronomical instruments further underscores its importance. Its steady emissions across multiple wavelengths make it an invaluable standard for testing and calibrating telescopes and detectors. This reliability ensures that observations of other celestial objects are accurate and comparable, enabling astronomers to build a cohesive understanding of the universe. As we look to the future, the Crab Nebula will undoubtedly remain a cornerstone of astrophysical research. Advances in observational technology, such as the upcoming generation of space telescopes and ground-based observatories, promise to reveal even more about its structure and behavior. Meanwhile, theoretical models will continue to evolve, incorporating new data and refining our understanding of the physical processes at play. But beyond its scientific value, the Crab Nebula represents something more profound. It is a reminder of the universe's capacity for both destruction and creation, a symbol of the interconnectedness of all things, and a testament to humanity's enduring curiosity. Its story, one of a star's death giving birth to new forms of matter, energy, and understanding, is a microcosm of the larger story of the cosmos itself. The Crab Nebula challenges us to look deeper, think bigger, and embrace the unknown. It is a beacon of discovery in a vast, mysterious universe, a reminder that even in the aftermath of cataclysmic events, there is beauty, complexity, and the potential for new beginnings. As we continue to study this remarkable object, it will undoubtedly yield more secrets, inspire new questions, and deepen our appreciation for the wonders of the cosmos. The study of the Crab Nebula is not only about understanding a single astronomical object, it's about piecing together the story of the universe itself. At its core, this remnant embodies the life cycle of stars, the intricate dance of matter and energy, and the interconnectedness of cosmic events over billions of years. Its continuing evolution invites us to imagine the far-reaching consequences of these phenomena, and how they shape the universe we see today. One of the most compelling aspects of the Crab Nebula is its ability to continually surprise and challenge astronomers. Each discovery brings with it new questions, and the nebula has become a proving ground for theories in astrophysics. For example, its gamma-ray flares have puzzled scientists for years. The energy involved in these events seems to defy the limits of known physical processes, pushing the boundaries of our understanding of magnetic fields and particle acceleration. These flares occur unpredictably, offering only brief windows of opportunity for observation and analysis. As such, they are a reminder of the dynamic and often chaotic nature of the universe. The pulsar at the heart of the nebula is another focal point of research. Rotating at an astonishing 30 times per second, the pulsar is a dense, magnetized remnant of the original star's core. Its magnetic field, billions of times stronger than Earth's, channels beams of radiation that sweep across the sky like a lighthouse. When these beams align with Earth, they produce the characteristic pulses that give pulsars their name. The precision of the Crab pulsar's timing rivals that of atomic clocks, making it a natural laboratory for studying the fundamental laws of physics. The pulsar's magnetosphere is a highly complex environment where particles are accelerated to nearly the speed of light. These particles create the nebula's striking synchrotron radiation, which emits across the electromagnetic spectrum. Understanding the mechanisms at work in the pulsar's magnetosphere is a significant challenge, as it involves extreme conditions that cannot be replicated in terrestrial laboratories. Yet, these studies are crucial for unlocking the secrets of particle acceleration, which has implications for everything from cosmic rays to the jets produced by black holes. The Crab Nebula also holds a special place in the field of spectroscopy. By analyzing the light emitted by the nebula, scientists can determine the chemical composition of its gas and dust. This information provides insights into the processes that occur during a supernova explosion and the subsequent evolution of the remnant. The nebula is rich in heavy elements like carbon, oxygen, and iron, materials that were forged in the heart of its progenitor star. These elements are the building blocks of planets and life, highlighting the nebula's role in the cosmic cycle of matter. In addition to its scientific significance, the Crab Nebula continues to inspire awe and wonder. Its intricate, web-like structure, glowing filaments, and dynamic behavior make it one of the most photographed and studied objects in the night sky. These visual characteristics are not just aesthetically pleasing, they are also scientifically informative. The filaments, for example, trace the paths of magnetic fields and shockwaves, revealing the nebula's internal dynamics. The interplay of colors in its images corresponds to different wavelengths of light, each representing a unique physical process. As we gaze upon the Crab Nebula, we are reminded of the power and beauty of the cosmos. The light we see today began its journey nearly 1,000 years ago, carrying with it the story of a star's violent death and its transformation into a source of energy and wonder. The nebula is a snapshot of a single moment in cosmic history, yet it connects us to the broader narrative of the universe. Looking to the future, the Crab Nebula is poised to play a central role in the development of new observational technologies. As telescopes become more advanced, they will be able to capture even finer details of the nebula's structure and behavior. For instance, the James Webb Space Telescope, JWST, and next-generation ground-based observatories like the Extremely Large Telescope, ELT, promise to revolutionize our understanding of objects like the Crab Nebula. These instruments will provide unprecedented resolution and sensitivity, allowing scientists to probe the nebula's innermost regions and uncover its most elusive secrets. Moreover, the Crab Nebula serves as a model for studying other supernova remnants and pulsar wind nebulae throughout the universe. By comparing its properties with those of similar objects, astronomers can identify patterns and variations that shed light on the underlying physical processes. This comparative approach is essential for building a comprehensive picture of stellar evolution and the mechanisms that drive the universe's most energetic events. In many ways, the Crab Nebula is a gateway to understanding some of the most profound questions in astronomy. How do stars die? What happens to their remnants? How do the elements necessary for life spread across the cosmos? These questions are not just scientific, they are deeply human, reflecting our desire to understand our origins and our place in the universe. Yet, for all that we have learned, the Crab Nebula remains an enigma. Its complexity defies easy explanations, and its dynamic nature ensures that it will continue to surprise us for years to come. Each new discovery adds another layer to our understanding, but it also reminds us of how much we have yet to learn. In this sense, the nebula is a microcosm of science itself, a never-ending journey of exploration and discovery. The story of the Crab Nebula is one of transformation and renewal. It is a story that began with a cataclysmic explosion nearly a millennium ago and continues to unfold before our eyes. It is a story that speaks to the resilience of the universe, the interconnectedness of all things, and the power of human curiosity. As we continue to study this remarkable object, we are not just learning about the cosmos, we are also learning about ourselves, our history, our future, and the infinite possibilities that lie beyond. The Crab Nebula stands as a vivid testament to the cycle of creation and destruction in the cosmos. It reminds us that the universe is in a constant state of flux, with processes that dismantle, transform, and rebuild in ways that sustain its continuity. Even as a remnant of a cataclysmic event, the nebula has become a hub of activity, a place where matter and energy interact on scales that defy imagination. The pulsar at the heart of the nebula is a key piece of this cosmic puzzle. While it may appear as a faint speck in the vastness of the nebula, its role is monumental. It powers the Crab Nebula's brilliance, emitting electromagnetic radiation that spans the spectrum from radio waves to gamma rays. The pulsar's rapid rotation and intense magnetic field produce winds of charged particles that collide with the surrounding material, creating the luminous synchrotron radiation for which the nebula is famous. These interactions between the pulsar wind and the nebula's gas and dust are a fascinating area of study. Scientists are particularly interested in the mechanisms that generate the nebula's gamma-ray flares, which are among the most energetic events observed in our galaxy. These flares appear to originate from small, localized regions within the nebula and can outshine the entire structure for brief moments. The exact processes behind these emissions are still a subject of debate, but they are thought to involve magnetic reconnection, a phenomenon in which magnetic field lines break and reconnect, releasing enormous amounts of energy. The gamma-ray flares of the Crab Nebula have significant implications for our understanding of high-energy astrophysics. They challenge existing models of how particles are accelerated to near-light speeds and offer a glimpse into environments that are otherwise inaccessible. Observing and analyzing these flares requires cutting-edge technology, including space-based observatories like the Fermi Gamma Ray Space Telescope and ground-based arrays like the Cherenkov Telescope Array, CTA. These instruments are crucial for capturing the fleeting signals from such transient events, enabling scientists to piece together the conditions that give rise to them. Another intriguing feature of the Crab Nebula is its intricate filamentary structure. These filaments are composed of cooler gas that emits optical and infrared light, providing a stark contrast to the surrounding synchrotron emission. The filaments are remnants of the progenitor star's outer layers, which were ejected during the supernova explosion. They are rich in elements like oxygen, carbon, and nitrogen, offering a detailed record of the star's composition and the processes that occurred during its final moments. The arrangement and dynamics of the filaments reveal much about the nature of the explosion that created the Crab Nebula. They appear to be organized into complex networks, shaped by shock waves and magnetic fields. Some filaments move outward at high speeds, while others seem to be caught in turbulent motions, creating a chaotic yet ordered pattern. Studying these structures helps scientists reconstruct the sequence of events that led to the formation of the nebula, shedding light on the physics of supernovae. The Crab Nebula also serves as a natural laboratory for studying cosmic rays, high-energy particles that travel through space at nearly the speed of light. The nebula is thought to be a source of these particles, which are accelerated by shock waves within the pulsar wind. By observing the nebula across different wavelengths, scientists can trace the paths of these particles and identify the conditions that enable their acceleration. This research has broader implications for understanding the origins of cosmic rays, which play a significant role in shaping the interstellar medium and influencing star formation. As technology advances, the tools available for studying the Crab Nebula continue to improve. Instruments like the Hubble Space Telescope, the Chandra X-ray Observatory, and the Atacama Large Millimeter/Submillimeter Array, ALMA, provide unprecedented levels of detail, allowing scientists to probe the nebula at multiple wavelengths. These observations reveal new features and phenomena, offering fresh insights into the complex interactions taking place within the nebula. The Crab Nebula also serves as a benchmark for testing theoretical models. Its well-documented history, detailed observations, and dynamic behavior make it an ideal subject for simulations and computational studies. By comparing theoretical predictions with actual data, scientists can refine their understanding of the processes that govern supernova remnants and pulsar wind nebulae. This iterative process of observation and modeling is at the heart of scientific inquiry, driving progress in the field of astrophysics. One of the most profound aspects of the Crab Nebula is its connection to human history. The supernova explosion that created it was observed by astronomers in 1054 CE, leaving a record of its appearance in ancient texts and artworks. This historical context adds a unique dimension to the study of the nebula, linking it to the broader narrative of human curiosity and exploration. It is a reminder that the quest to understand the universe has deep roots, stretching back centuries and transcending cultural boundaries. Today, the Crab Nebula continues to inspire new generations of scientists, artists, and dreamers. Its ethereal beauty and dynamic nature make it a favorite subject for astronomers and astrophotographers alike. Its scientific importance ensures that it remains a focal point of research, pushing the boundaries of what we know about the cosmos. In the grand scheme of things, the Crab Nebula is just one of countless supernova remnants scattered throughout the universe. Yet, its unique characteristics and well-documented history set it apart, making it a cornerstone of modern astrophysics. It is a vivid reminder of the cycles of creation and destruction that shape the cosmos, and a testament to the power of human ingenuity in unraveling its mysteries. As we continue to study the Crab Nebula, we are not just exploring a single object, we are delving into the fundamental processes that govern the universe itself. From the life and death of stars to the acceleration of cosmic rays and the interplay of matter and energy, the nebula offers a window into the mechanisms that drive cosmic evolution. It is a story that is far from over, with each new discovery adding another chapter to our understanding of this remarkable remnant. The Crab Nebula's story is a journey through cosmic extremes, revealing the delicate balance between chaos and order in the universe. Its persistence over nearly a millennium since its creation serves as a reminder of the longevity and interconnectedness of celestial phenomena. The pulsar at its heart, a spinning neutron star with an intense gravitational pull, is an extraordinary entity that continues to shape its surroundings in profound ways. At its core, the pulsar is an engine of incredible efficiency, converting its rotational energy into electromagnetic radiation. It rotates approximately 30 times per second, a speed that would be unthinkable for any macroscopic object, yet is stable enough to act as a cosmic lighthouse. This rapid rotation generates immense magnetic fields, thousands of times stronger than anything we can replicate on Earth. These fields are responsible for the high-energy jets and wind of charged particles that sculpt the nebula into its distinctive shape. The interaction between the pulsar wind and the material in the nebula generates a variety of phenomena that challenge conventional understanding. For example, the shock waves produced by these interactions create regions of turbulence and heating that accelerate particles to relativistic speeds. These particles then emit synchrotron radiation, a process in which their rapid spiraling around magnetic field lines produces light across the electromagnetic spectrum. The Crab Nebula is one of the brightest sources of this radiation, making it an invaluable object for studying the physics of high-energy environments. One fascinating aspect of the nebula's synchrotron radiation is its persistence and variability. While the nebula has been emitting light for nearly 1,000 years, researchers have noted sudden flares in its brightness that can last for days or weeks. These flares, observed in gamma-ray wavelengths, are among the most energetic events in the galaxy. They are thought to arise from magnetic reconnection events, where the intense magnetic fields within the nebula suddenly realign, releasing a tremendous amount of energy. Such occurrences are not only spectacular but also offer crucial insights into the behavior of plasmas in extreme conditions. The Crab Nebula's intricate network of filaments also provides a rich field of study. These structures, composed of heavier elements ejected during the supernova explosion, are arranged in patterns that reflect the chaotic violence of their origin. By analyzing the composition and motion of these filaments, scientists can reconstruct the star's life cycle and the sequence of events that led to its explosive death. For instance, the abundance of elements like oxygen, carbon, and silicon in the filaments points to nuclear fusion processes that occurred in the progenitor star's core before the explosion. The movement of the filaments, which varies from rapid outward expansion to slower, more chaotic turbulence, reveals the complex interplay of forces that shape the nebula. One particularly striking feature of the Crab Nebula is its ability to act as a cosmic particle accelerator. The pulsar wind creates shock waves that accelerate particles to energies far beyond what can be achieved in Earth-based laboratories. These cosmic rays, primarily electrons and positrons, provide a unique opportunity to study the physics of particle acceleration. Observing how these particles interact with the nebula's magnetic fields and radiation environment allows scientists to test theories about similar processes occurring in more distant and less accessible parts of the universe, such as active galactic nuclei or gamma-ray bursts. The Crab Nebula also serves as a natural calibration source for astronomical instruments. Its brightness and relatively stable emission across a wide range of wavelengths make it an ideal reference point for telescopes and detectors. This role has been particularly important for space-based observatories like the Hubble Space Telescope, the Chandra X-ray Observatory, and the Fermi Gamma-ray Space Telescope. By comparing observations of the Crab Nebula with theoretical models, astronomers can fine-tune their instruments and improve the accuracy of their data. Despite centuries of study, the Crab Nebula continues to surprise researchers with its complexity and dynamism. Advances in technology and methodology have opened new avenues for exploration, allowing scientists to probe the nebula in ways that were unimaginable just a few decades ago. For example, polarization studies of the nebula's light are providing insights into the geometry and orientation of its magnetic fields, while high-resolution imaging is revealing previously unseen details of its structure. The nebula's relevance extends beyond astrophysics, influencing fields as diverse as plasma physics, nuclear chemistry, and even philosophy. It serves as a vivid reminder of the interconnectedness of scientific disciplines, demonstrating how understanding one phenomenon can illuminate others. The Crab Nebula exemplifies the idea that the universe is a vast, intricate system where even the most distant and exotic objects can teach us something fundamental about our own existence. In essence, the Crab Nebula is more than just a remnant of a long-ago supernova. It is a living, evolving laboratory for the study of the universe. Its pulsar, filaments, and dynamic emissions are pieces of a cosmic puzzle that scientists are still working to solve. Each discovery about the nebula adds to our understanding of the fundamental forces that shape the cosmos, from gravity and electromagnetism to nuclear and quantum processes. As we continue to observe and study the Crab Nebula, we are reminded of the vastness and complexity of the universe. It challenges our understanding, fuels our curiosity, and inspires us to look deeper into the cosmos. It stands as a symbol of the interplay between destruction and creation, chaos and order, a timeless testament to the beauty and mystery of the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.